Okay. Okay. So the SIMCA is we're going to do afterwards, and we're going to do it step by step, and hopefully we'll all follow. If you do not, please stop. Let me see if we can assist you. Otherwise, the recording will also be available. So if you then want to check it later on, then you can see if that's if you cannot get what we getting on the SIMCA. And then after that, we'll do the interpretation. So we've showed you yesterday examples of what you can do with the data and what are the capabilities and what kind of answers you get from this analysis. And we're going to show you a few examples of how to interpret the data, what to look out for, and then we'll end off for the day. So Flonipeni is one of the PhD students here at UNISA. He's been doing quite a bit of metabolomics for his master's as well as his PhD. So he's also quite advanced with his PhD project already. So he's still fresh in using these programs. So he's going to start this morning with Mestranova. So with that, I'm going to hand over to Flonipeni.
Thank you, Prof Prinsloo. Good morning, everyone. My name is Prof Prinsloo, as said, is Flonipeni Msomi, and I will be taking you guys through the pre-processing of your data. From Tuesday, you've learned so much, and everything has been explained. Sample preparation, and then NMR data acquisition, whereby you run your data on the NMR. Now you have run your data on the NMR. What's next? The next step is to pre-process your data. So I guess you managed to download the evaluation of Mestranova software.
Yeah.
How many of you? Did you manage?
It's collective approach.
Okay, so just to combine, so we're talking about combining the exercises just now for the two workshops.
Can we just ask members to mute? Okay.
Okay, thank you.
Dr. Msomi, if you can maybe just increase your volume a little bit as well.
Okay.
Thank you.
So now I'm going to share my screen and show you how to pre-process your data, your raw data, FIDs that you get from NMR. Can you see my screen?
Yes, I can.
Okay, is my voice loud enough now?
Yeah, that's fine.
Yes, it's audible.
Okay, thank you. Guys, when you go to your Mestranova software, this is the home page that you see. As you open your Mestranova, this is the home page. Now you wanna take your raw data, your FIDs from NMR to pre-process, align the peaks, your peaks. You have to, do your baseline correction, your phase correction, so that your peaks are well aligned, and then you start build up your NMR data that will be run on SIMCA. So now we will take our first sample and run it and pre-process it. The first thing that you do on your home page, you go to File, and then from File you open. Now I'm going to my file whereby there are raw NMR samples, the FIDs. So these are my samples that I've run on NMR. Now we're going to take the first sample, open the first sample, and then you go to Proton FID. And then you select FID. Remember, when you run your samples on NMR, what you're looking for from your sample is the FID. So you select FID, you open it. It will look like this on your software. And then the first thing that you do on your sample, you do the referencing. You right click, and then there is reference. You reference the TSP peak. And the TSP peak is there, and then you take your cursor, you put it there. It must be referenced, and you right click on it. And then next to new shift, it must be referenced. It must start at 0.00. Make sure that you put 0.00 there, ppm. That's where it's supposed to start your peak. And then the next one, you normalize. When you do normalize, you go on processing, there on top, and then there are 3 blue dots there, more processing, whereby you select normalize. And when you normalize now, you reference your y-axis. You look at the largest peak, it has to end at 100. So already the software has selected 100 for you, the value of 100 there. Only what you have to do is to click OK. Then you can see your largest peak now. It's on 100 on the y-axis. Then the third one, you right click for phase correction now. You go to phase correction. Fortunately, the new version of Mastronova, it is added, the automatic options now, where you phase correct automatically. You just select automatic phase correction. It has been corrected, and then you right click again. You do the baseline correction. Your baseline correction that you're supposed to select is full automatic, which is retake a smoother. We select it. And then when we are done with the baseline, we started with referencing the TSP peak. We normalized the y-axis peak on the peak, and then phase correction, baseline correction, and then now we go to file and save as. Firstly, we save as the NMR CSV file. After saving as the NMR CSV file, we close. We do not close, remember, we do not close the whole software, but we close the spectra, the current spectra that we are working on, which is here on the tab. We close, and then it will show you this box. The document has been modified. Do you want to save changes? No. And then you go to file and open again your NMR CSV file that you've just saved. So you go to your sample, the one that you were working on, and then you click on Proton FID again. Now it has saved the NMR CSV file. You open the NMR CSV file. Now you do the binning. where you choose the area from, 0.00 to 10. Go to processing, and then more processing. There is binning, the option of binning there. You click on it. So on this box, on the box of binning, it will show you, these already, the software has done it for you. Under the full spectrum, your spectrum, it starts from 0.00 ppm to 10 ppm. Remember, in your integration region, it has to be on 0.04 ppm. Then you click OK. But if it's not like this, you will have to change it. You have to do it manually and make sure that your full spectrum starts from 0.00 to 10. Now we click OK, binning. Excuse me.
Okay, I've muted them, Dr. Msombi.
Thank you. Okay, we've done now the binning. After doing the binning, we go to File, and we save as the Mastranova file now, the Mastranova document. And then again, we go to File, we save as the NMR CSV matrix transposed file, which is there at the end. Now, when you save the NMR CSV matrix file, because already you have saved the Mastranova file, which is written as Proton 1. You see here, the moment you save, you select NMR CSV matrix file, it's Proton 1. You just have to change the name, the file name. Maybe, let's say here 1A, because it will be saved in your FID, in your whole sample. So you want to save them differently. Give them different names. We save. And then after saving, you are done with your sample, your first sample, pre-processing your first sample. Now you go to Excel sheet. You want to build up your NMR data. You open your fresh Excel sheet. Now you are going to open your FID, the one that has been pre-processed. You go to File, you open, browse. Now you go to your NMR file, the one that you are working on. This is the first sample that we are working on. Do the same thing again, open Proton FID. Okay. When you see it like this, let me go back. You have to make sure here at all access files that it's all files, not access files. It has to be all files. Otherwise, you won't see your matrix file that you are looking for. All file, and then you open Proton FID. You see now your sample, because you have been pre-processing, you have your Mastranova file, you have your CSV file, you have your matrix file. This is the matrix one that we saved after binning. We gave it a new name, 1A. Now you open it on your Excel sheet. It will be transported to your Excel sheet. And then your Excel sheet will look like this. This is your first sample. You see, when you were pre-processing, you referencing, making sure that it's your peak starts at 0.0 to 10, and your width 0.04. Now it can show you here that it starts at 0.04. If it doesn't come out like this, it means there's something that you did not do. There's a step maybe that you did not do when you were pre-processing. It should start here. You should look at A1 on your cell, A1, 0.04, and then just scroll right to the end and check if it ends at 10. That's how your peak it should be. See, it ends at 10, from 0.04 ppm to 10 ppm. That is your first sample that you have pre-processed. Now we are going to do the second sample. We are going to pre-process the second sample and build up, you know, the NMR data on Excel. Let's do the second one. Go back to your software. Now you close the old one. You open the second sample. So we are done with the first one. This is the second one. Proton FID. Open the FID. Now this is your spectra. It looks like this. As you can see before it is pre-processed. The first thing to do, you reference your TSP peak, right click, reference. You select reference and then you take your cursor.
Dr. Msomi, I have a question for you while we are here. Are you able to hear me?
Yes, I can hear you.
Okay, so when you open the FID at this point, will the peaks always be facing up or will some of them be down sometimes?
No, most of them are facing up.
Will face up.
Yes.
Okay.
Yes, they are facing.
And so the TSP is the internal standard that was in your sample, right? So you're going to reference against that.
Yes.
Okay.
And it has to start at 0.00 because sometimes it is not aligned correctly. It is maybe at 0.01, but it has to be 0.0.
So then you put the cursor at 0 to force that peak to shift to 0.
Yes.
All right.
Put the cursor after selecting a reference. And then when you put the cursor, you right click
Okay.
on it, and then it will show you. Then you next to new shift, you put 0.0.
Can I just ask participants to mute their mics, please?
Okay.
Thank you.
Thank you. Then we've referenced the TSP peak. Now we go to processing. Then under processing, more processing, you select normalize. Now your y-axis, click OK, the value has to be 100. Now, as you can see, the largest peak on the y-axis, it's on 100. And then the third step is phase correction. You right click now for phase correction. There is phase correction. You select automatic. You right click again.
Dr. Nsombi, another question at this point, just while we are here.
Yeah.
So the phase correction, could you do it manually as well?
Yes, you can do it manually.
Okay. So when you do it manually, does that just mean you shift the mouse or how do you do that?
This is the new one, actually, the new software. On the old software, you could do it manually.
Okay.
Now it is automatic on the new software.
Okay.
Yes.
All right.
Phase correction, this is the automatic. And then the baseline. So the baseline you can select, you can do it manually as well. As you can see, the method here is we take a smoother, and there are other methods. But for this one, we select we take a smoother.
Okay.
So you can do it automatically as well, as the option is already there.
Okay.
Okay, now we've done the baseline correction. We save file, save as the NMR CSV file first. You go there, look for NMR CSV file, you select it, you save. Then you close your current spectra and you select no. Then you go to file and open again your CSV file. Here's my CSV file. No, let me make sure that I'm doing the right sample, the second sample that I was working on. Yeah. There is your CSV file. You open it again. And now you do the binning processing. Select processing, more processing. Do the binning. Already on the box, it is selected for you on the full spectrum, 0.00 ppm to 10 ppm. And then in the integration region, the width is 0.04 ppm. Okay. See how it looks now. The peaks have changed after binning. After binning, you save now. Save as the Mastronova document. Again, you save for the last time as the matrix file, NMR CSV matrix file. Select, and then you change your name there, file name. Let's say 2A. Now we have saved. Then you go to your Excel sheet again. File. You open. Go to your NMR data. Go to your second sample that you were running. FID. And then you see all your files have been saved as you were saving pre-processing and saving as first as an NMR CSV, Mastronova file document, and then NMR CSV matrix. They are all there now in your sample. Now you select your NMR CSV, your NMR CSV matrix. You transport it to your Excel sheet. There it is, your data now. It is correct, beginning from 0.04 to 10. You have to check each and every for each and every sample if it is okay, if your peak is beginning from 0.04 to 10. And then because you are building your Excel sheet, your data, now you can copy this one for the second sample. And then you're going to edit on your first. Okay, sorry about that. No, all right, let's do the third sample and the fourth sample, then we can combine them and then build up on Excel and see, you know, how to, you just copy and paste. You go to the first sample, second and third, you copy everything. It's up to you. You can do it, you know, by pre-processing each sample first, and then you leave it like that, go to the last sample, and then when you are done with all your samples, then you can start now opening one Excel sheet whereby you transport, you copy from each sample and then build up one Excel sheet. So let's do the third sample.
Dr. Msomi, a question at this point. So we're going through a few samples so that people that have entered in a little bit late can follow as well. But does the software not allow for you to sort of do type of a batch analysis where you can sort of pull in a few samples at a time?
Yeah, it does allow you.
Okay.
It does allow you, yes.
All right.
Okay, let's do the third sample, another sample. Let's close. Open. Open the third sample, Proton 1 FID, and then we select FID. And then we reference the TSP, pick, right click, select reference, and then put your cursor on the TSP peak, which is close to 0, and you right click on it. It is 0.00 ppm. And then it has been referenced. Then you go to processing. The second step is to normalize. You go to processing and it's found on more processing. There is normalize. The software already has selected for you. Here we normalize, the largest peak, it has to end at 100. The value is 100 already. Click OK.
Sorry, Employee Penny, yeah. Normally your TSP peak should be the highest, so we normally say normalize to your TSP peak, because the highest peak is your water, but that is not standardized. Sorry, I just had to just quickly check that, but I've put it on the in that notes that was sent to everyone. So just make sure that the normalization is on the TSP peak, not the largest. So if you go to normalize and select there, then you'll select peak at 0.00. Just go to normalize again.
Okay, thank you.
Yes.
Normalize.
Yeah, just go to normalize. Yeah. The largest peak, just go to that one. And then just say peak. Go down. Yeah, see, and then you select at 100 at 0.00, and that is fine. Then it's going to normalize according to your TSP peak. If your TSP peak is the largest peak, that's fine, especially if you added like 1%, 0.1% TSP. If you recall on Monday when we did the sample preparation, if you add more TSP, then your TSP peak should be the largest one. But in this case, the TSP is quite short and small. So then it should be just change to the normalization of the peak at 0.00.
Okay. Thanks, Prof. And then after normalize, the phase correction, automatic, and then the baseline correction. So we take a smoother, and then file. We save as the NMR CSV file. And we close. You want to save changes? No. We open. Sorry. File. Open. We open our CSV file. Processing, and then we do binning. and everything is fine. Spectrum is from 0.00 to 10, and the width, the bin width is 0.04. Okay.
Dr. Msomi, at this point, that width that you choose, the 0.04 ppm, is that standard, or can you play around with the width that you want to use?
No, it is standard.
Okay.
Yeah, it's quite standard. Most people use binning of 0.04. If you check the publications,
Okay.
you can change it. If you make a smaller bin or a bucket, then your data set is just getting larger and larger.
Okay.
So what the people found that developed these protocols was that 0.04 is a manageable size for the bins.
Okay.
So all the peaks in that region from 0 to 0.004 will be combined to give you one value.
Okay.
So and that gives you, if you work from 0 to 10, to about 273 values. So if you make the bin smaller, then you're just going to increase the number of values.
Okay.
So you can, depending on your sample, but this is quite a good bin number to use to get a proper analysis at the end. So I think to start with, the recommendation is to start with use 0.04.
Okay. If I may just add, for those of you who are probably new to NMR or the concept of binning, if I can use an analogy similar to a slice of bread, right? So we go from the first slice to the last slice of your bread. So we go from 0 ppm to 10 ppm. And so what binning is basically slicing the spectra into slices, similar like how you would slice a loaf of bread. And we then go into each of those slices. That bin will be a region that we will inspect. So I hope that is clear to everybody. So we're just basically slicing the spectra into bits and pieces, and that's how you get those numbers in your Excel sheet. So you can basically see each of those regions as a slice of bread.
I love the example.
Thank you.
Yeah.
So
It's an example.
we can continue, Dr. Msomi.
Okay, then we've done the binning. We save as. So let me start again. File, save as. Save as the Master Nova document first, and then lastly you save as NMR CSV matrix transposed. Let me say 3A. Okay, let's do the last one for the fourth sample. Okay, for those who have just joined us. Now you go to File. This is your home page. Go to File, Open. Go to your fourth sample, Proton FID. Open your FID. And reference. Click on the peak. .0, and then processing. We go to normalize, more processing, normalize, and then we select peak here. The value is 100. Okay. And then after normalize phase correction, you right click on your screen, anywhere on top of your spectra here, phase correction, you select automatic, and then the baseline correction, full automatic, which is you take a smoother, and then you go to file, you save as your NMR CSV file, save, and then you close it, no, select no, you go to file and open again your NMR CSV file. Open your NMR CSV file. And you go to processing and do the binning. More processing, binning. Binning here is okay. Everything is okay. Start from 0 to 10. Okay. Then you go to file. You save as the Mr. Nova document, second, and then the third, the last one, you save as NMR CSV matrix transposed. Let me give it 4. Yes, now you have pre-processed your 4 samples. Let us go to Excel. Now on Excel, you open, browse. Let's do the first sample now. Open Proton FID. There is your NMR CSV matrix, the transposed. Yeah, this is your first one. It looks like this on Excel. Then you can open the second one and build up to this Excel sheet, whereby you're going to build up from the first sample up to your last samples. So when you are done everything, when you pre-processed all your samples, then you can now come and open them and you copy and paste them here, building up your NMR data to be taken now from here to Simca. So as you can see here, it starts, the peak starts from 0.04 to 10. And then let's go to the next one. The second sample to A. Let's paste it here. And then even the third one, it's going to be like that. You open and then you paste it. You build up your data. And then these first two columns, you can delete them. Remove them. Okay, you can do that maybe at the end, but following from the second sample, and then you give each other underclass the name if it's one, and then it's two, depending on the name of the samples, you know, what you have given to your samples. And then let's do this the third. Sorry, my laptop looks like it's freezing.
I think, can I just add something as you are fixing the laptop?
Okay.
Yes, I just wanted to say to the new people that this may seem very confusing, but once you get it right, you will not have a problem. So this is what we used to do. We used to know how many saves are there. So we know that the first saving after you have pre-processed the raw data and you've normalized and
I can't hear you now, Dr. Nemadodi.
I think she's lost connection.
Oh, okay. Then this is the third one.
But I think what she was trying to say is just that because you save your files in different folders and stuff, it might be a bit much, especially when you're working with a lot of samples. So it's just a matter of getting used to the software and knowing where your files are.
Okay. Thank you. And okay, now I will just show you the one that has been done already, how it should look like before you take it to Simca. Like this is the one that has been done, the database that has been, you know, developed, all the samples that have been pre-processed.
Dr. Msomi, can I just mention on the Excel sheet that you currently worked on right now, if you can just go back to that one. If you can just show it quickly. So if you guys remember the first two samples, we normalized incorrectly, I think, to the highest peak, right? Which was water. And we should actually have reference to your TSP. So look at how different those numbers are if you normalize to one thing versus the other. So make sure that you are normalizing to your TSP when you are doing this. So we corrected that. And Prof Prinsloo will do another example as well where the TSP peak is a little bit higher. So notice how those numbers or values changes. Okay.
Yeah,
thank you.
That's a bit of a catch situation there. Many people just use that setting that says largest peak, and they just assume that the TSP is the largest. But if you have a bit of residual water, if it was a bit a rainy day or something, you have a bit of water coming into your sample, then, for instance, your water can go a bit higher. And so just check your sample before you do that. If your TSP is the largest, then it's fine. Then you just continue largest peak. Otherwise, you have to select that other one on peak.
Another question though, Prof. Should you not have suppressed your water at this point as well?
You see, you can do a suppression of your water on the NMR analysis when you go to your equipment. Then you do the preset setting where they suppress the water peak. If you have not done that, when we go to Simca, I will show you there where we then just exclude that region of the water peak. So,
Okay.
so I'll show that later. The same with if you use chloroform or if you use methanol as well, then you will take out those regions of those solvent peaks.
But if you do it at that point, would that water peak not have masked some of your metabolites at this point so that you don't actually see them in your Excel sheet?
Yes, sometimes it can do that, yeah. So, so the best is actually to use the preset setting to make sure that your water peak is not overlapping some of your peaks. But yeah, then also this you can, yeah, maybe just suppress the water peak, yeah.
We have a question from William. Yes, please unmute.
Hi, hello, good morning. I just wanted to ask about the spectra itself, that this normalization from 0 to 100 on your y-axis. Is this on assumption that your largest peaks are equal? Because in terms of quantification, I'm assuming that there's going to be some aspect of quantifying those peaks. Isn't that going to influence, especially if the largest peaks aren't exactly the same size? Because at first, you would have those values going to the tens of thousands, and that obviously is variable between samples. So in terms of quantification, isn't that going to have some significant influence on the results later? Thanks.
Yeah, exactly. That's why it's important to check that you normalize on the TSP. So if TSP is not your largest peak, it should be normalized on TSP. Remember, when we showed the sample preparation on Tuesday, we added TSP at a specific concentration to your solvent. So if you work accurately, that you weigh out your TSP accurately, and you pipette exact amount to your solvent after your sample, then your TSP peak should be the same in all your samples. But just to make 100% sure, we normalize the TSP to 100, so that all your samples, your quantification is then done according to your standard, which is your TSP, and that should be 100. So that is why I say be careful when you select the largest peak. It can be throwing out all your results if you do not check that your normalization is on the TSP. That's very important to check that.
So in the case of not having the TSP there, I'm doing it with some of my spectra. I wish I could share it. But say, for example, you don't have a peak there, because I think the presenter also showed where he has a very minimal peak there by 0, so for TSP. Yeah. In that case, would you just keep the raw data as it is and start processing from there? So not normalize to 100 with the largest peak.
Yeah, then what people sometimes do is to select if you know what you're working with. So people will go and select, for instance, a succinate peak and normalize to that. You see, if you do not normalize, then it will be difficult to quantify. If you do not have a standard in your sample somewhere that you know that is a given concentration, you cannot quantify the other peaks. So that's fine to just look at your profile there, but you won't be able to quantify it then.
Okay. All right. Thanks, Prof.
Can I just add on this? So usually you would have to have a internal standard, but in the case where it might be low or you have stuff binding to it, what you can also do is your sample type. So internal standard, you need to go look at what are the conditions of choosing an internal standard, right? It needs to be something that you will not find in your sample, more or less similar, but something that you don't expect to find in your sample. And if for instance, formic acid you don't usually find in the sample type that you're working with, you can then use that as your sort of internal standard in that data set, right?
Yes.
And I think that's what Prof Prinsloo was also explaining with the succinate example. Yeah.
Yes. But just note that you will not know what was your, for instance, the succinate or that internal one that you select if you don't know the concentration of that specific peak, you won't be able to do quantification. So you can kind of standardize all your samples according to that one, to that peak, but if you don't know the concentration of that specific peak, you won't be able to quantify. So you need to have a standardized or a standard somewhere in your sample that you add at a specific concentration to quantify at the end.
Maybe, Prof, if you do have maybe another sample whereby it will show the TSP as the largest peak, maybe.
Yeah, I have quickly looked at the sample, so I'm going to show that now. Can
I, Dr. Msomi, can I just ask, your TSP, was it very low or was it completely absent when you were doing it now? Was it just low?
Yeah, you see those samples, we realized that the NMR files, this is another thing with online, the NMR files you cannot email. When you email, some of the information got lost. So that's why we asked to go and have a look at that data set. But that is not his file. So we kind of try to have a balance here on just getting files that you can have a look. So let me show you this example.
Okay, but it's good that we get to see, because I think in some biological samples you will have instances where some stuff might bind and you don't get such a high TSP peak.
Yes.
TSP peak should be clear. So if you look at this sample, you can see the TSP peak is quite clear, and it is at 0. If it's not exactly at 0, sometimes it's a little bit up or down, then you can use, for instance, your methanol peak or your water peak to just reference your sample. But in this case, you can see your TSP peak is quite large. And this is how it should be. So if your TSP peak is too small, then rather add more TSP to your samples. So there's some background noise. Is it coming with me?
Yes, I've checked, Prof. It's coming from you. All the other participants are muted.
Okay. Okay. So I'm just going to do that step on the normalization. Just show you if you do the TSP normalization to 100. See there it's at 230. So I have an older version, so sorry about that. So normalization here. So you're not going to select largest. It's sorry, wait. Let me just do the reference quickly. If the reference is also not at 0.00 exactly, then you won't. Then it won't pick up that peak. So just make sure this one is now perfect. And then you do your normalization. It's my best to just select peak. You see now it's going to 100, and this is what you want. So your TSP peak was added to a specific concentration to your solvent. If you pipette accurately, then you should have the same amount of TSP in all your samples. And then if you reference your TSP to 100, then all your samples should be this similar, and then you can accurately quantify your compounds later on. Okay, is this one more clear?
Yes.
Okay, and you can still see there are some peaks that are still larger than your TSP, and this is not even water. These are peaks in your sugar region. So these are peaks in your sample. So if you just select largest peak, you're going to, this sample will then be out. You won't be able to use this sample. So just make sure your TSP peak is exactly at 100. Then you'll be able to then all your samples, all the rest of the samples will be the same. And while I'm busy here, I saw there was a question on someone asking if you do batch batch processing. I'm not a supporter of batch processing, purely because if you have a sample where one of your, it's a different sample, or it looks different, or your analysis knows, I will show you later on where you have a sample where the resolution is not good, and you do a batch processing, and that sample is going with your other samples, it's going to throw out your analysis. So I prefer to, even if it takes a bit of time, this is very important to get your database 100% accurate, and to make sure that all your numerical values in your database is correct. Because if you have something wrong here, then it's going to throw out all your analysis later on, especially, and also your conclusions and your interpretation of your data. So spend a bit of time on this database to do this. So I prefer spending the time, even if it takes you 2 or 3 days, it will maybe save you months of time later on. Take the time and pre-process each sample separately.
Prof, there's another question. Yeah, can the same processing be done with other NMR software such as TopSpin or SpinWorks?
Yes, yeah, you will use the same. You will use the same principle. So you select your TSP and you will put that to 100. So all your software should be able to have that functionality to normalize, to reference your reference your TSP to 0.0, and or in the case if you use chloroform, your TMS, that is also at 0.0, and then to normalize your TSP peak to 100.
Yes, I'll just add on to that, Lirata. So you will always reference, and then you have to normalize. And then the other 2 things is obviously doing your phase correction and making sure that you've corrected that baseline. So all software should allow for that.
Yes, yeah.
Okay, we can proceed.
Okay, Penny, anything still from your side? Penny, I think maybe you're muted.
Oh, no, Prof.
Okay.
Nothing on my side. Thank you.
Yeah, maybe at this stage we can maybe just ask if there are any uncertainty about the processing still, because that's what your processing will entail, those 4 steps. Also, what I just want to highlight here and emphasize is when you've done your binning and you export your data to Excel, just check the data as well. Make sure the bins are exactly at 0.04, 0.08, and it goes right up until the last bin that you've selected. If it is 10, make sure that your values is going to 10, because if it's not going to, if your bins are not exactly 0.04, 0.08, then it means your alignment is slightly out, and then you don't get the same binning in all your samples. And you might see that also later on in your analysis, because your binning you're going to use for your contribution plot, which I'm going to show also later. And yeah, so if your bins are not exactly at 0.04, then you might include a peak or 2 from the bin next to it, which is not supposed to be there. So as I say, this database is extremely important. Make sure that it starts at 0.04, that it ends at 10, and make sure that all your bins are exactly aligned. And as I say, I prefer to do each sample separately, And then you also know if you have an outlier, then it's not because of anything else. It is an outlier because of the sample itself. So because once you have your database, once you have this Excel sheet database, then a lot of work can be done and a lot of data mining can be done. But if you're not sure your database is correct, then you'll always wonder what is happening with your data and with your analysis. So just make sure that this database is done 100% correctly.
Okay, do we still have questions perhaps? Prof, I know you are not a fan of the batch analysis, but do you think we can maybe run through an example of how it's done?
Oh, let's see. Penny, can you show that?
Can I just say something, Prof. Williams?
Yes, Dr. Lufuno.
Yeah, we tried the batch, and I understand. I think it's because Prof. Prinsloo, most people are just thinking that this is time consuming. When we started, we tried the batch and it just didn't work at all. It was just a mess. We ended up going to Professor Prinsloo and he said, "Why were you skipping the process?" So and you know, I've been getting a lot of I don't understand. You are not expected to understand on the first day. Remember, this is a process. So once you get used to you know, working on the raw NMR data that Marpeng is going to send to you, to send to you, and you start learning on the pre-processing. And I think Professor Prinsloo, maybe you need to perhaps at the end send, or maybe later today, there was a document, not a document as such, but there was one time that you sent us the steps that we need to follow. I don't know if you still have it, but you sent us the steps that we need to follow from raw data to pre-processing, the same thing that Msonipeni was doing, but it was on a written, like typed page. I think it was there were 2 pages that you sent us, Professor Prinsloo. Maybe it would be good for them to have something to refer to, like, you know. And then what we also used to do, I got cut when I was still talking. What we used to do, and it actually helped us. We knew that there were like 3 saves. Save as in, like, after your pre-processed, you will after your pre-process, after the baseline, then you need to save as NMR CSV. So we wrote that. Once you tick that, you go to the next one, which is now the binning. And then, of course, you check the 0.04. It's very important, like Professor Prinsloo has indicated. We cannot emphasize the importance of binning on 0.04. Once it's not there, you will see that it won't start on with a 0, but it will have another odd number like 5 or 2 or something. And then you know that your data is, I mean, your data is already corrupted. So once it's on 0.04, you see that everything else will start on 0. something something, and then the numbers, we even used to count that after 0.0, the numbers are either usually 5 or 7. It's such things, such tiny things that will make sure that your data is clean. And then, so the next save will be the Mastronova. So after you've saved, you must go and click the Mastronova or Matrix, because I think now things have changed. Now, if you want to make sure, that's how we used to do it. If you want to make sure that your data, the NMR CSV matrix has been saved correctly, when you check, it must have that Excel sign.
Yes.
Once it's on Excel sign, then you know that you are on the right track. That's how we used to do it. And then the very last one is NMR transposed. So we used to know that the transposed one is actually on the very last of the file names that you have to click. It's the very last one. The transposed is the last one, and it means that is the last one. Then from there, you now take and you're gonna have your data, and then you can either import to make sure that you are building on your data set.
Yes.
So these things are sometimes once you make a mistake, especially with the binning, I don't know how many trips we used to go to Professor Prinsloo. I don't know office. I have no idea. I'm sure he like each time, because you when you are working on it, you make a mistake, one mistake, either you skip the next step of saving, or you close where it says, do you want to close, and you say close, you say yes by mistake. It confuses the whole thing. So all the no's that Msolipeni was saying, that closing, and then it says no, you must just stick to that, because one mistake you are out, and then it means that you need to start again from scratch, from the raw NMR data all the way. So if you tell yourself that you just want to follow each step, in as much as we're saying that it may be time consuming, but once you get used to, and you know the important things that you need to follow without skipping, you get it right and you start moving. It will just flow. It will just flow.
Okay.
So the badge, Prof Williams, that one. That
No,
one is a mess.
We hear you. So I do agree to an extent, because these data sets gets very big, right? So I do agree that rather take it slow and do it step by step in the initial stages, so that you are confident that the matrix that you are working with is one that you are confident about.
Correct.
So can I ask, so Prof Prinsloo, Dr. Lufuno mentioned that there was like a 2-page document that sort of summarizes the steps. Or if you guys have it in sort of a flow chart, there's a request in the chat to please maybe just share a flow chart with this steps. So for example, step 1 is import your raw FID files. Step 2 is reference to TSP, making sure that and I think so step 2 is referencing to TSP. Step 3 is normalizing to your TSP. At the normalization step, I think make sure that you train yourself to go and choose peak. Don't go with the highest one, because you've seen now that TSP is not always the largest one. So just train yourself to always go choose peak, so that it forces you to go and click on your TSP as that the one to normalize against. Then the next step is your step 4 would be phase correction. Step 5 would be baseline correction.
Yes.
Obviously your binning would be the last one.
Yes. So this is the I'm sorry, Prof. This is the process that I was telling you about, that Professor Prinsloo, that just this is the one. Yes.
So
it shows step by step.
So Prof, I think we have it up there. Thank you. So what we will do is, if you can maybe just email it to me or Anza or Sikekeleto, and we will distribute it, or we can even, if there's time and you manage to save the document, you can even post it on the chat. So we will share that then.
Yeah.
Thank you.
So this one with 3 other files I've emailed this morning. I wanted to put it in the chat, but I can't manage to post it there. I will try again.
Okay.
But these 4 files I've emailed this morning, if you can just distribute it to the people.
Yes, I've received it.
It's one of those files that I've sent, because I've sent a similar one on the SIM card that we're going to do later on.
Okay.
So I don't know if that can quickly be emailed, then people will have it.
Anza Okeke, can you confirm whether you've emailed or sent it to your database?
Yes, it was emailed.
Okay.
Yes. So then you will have it in your emails. So you can just check that there.
For those of you who haven't received it as yet, perhaps just send an email to Anza Okeke and they will distribute it to you.
Yeah, and these steps, it's exactly what Mponipeni was saying. If you follow these steps exactly, you'll be fine.
Yeah. So I have this with you at all times by the side of your laptop or computer, wherever you're working. You will never go wrong at all.
Do we have any further questions? None? Is there anything from you, Prof? I think then we can take a break. It is now 10:17, and perhaps then just return at 10:35. Oh, there's a question in Dolo. Please go ahead and unmute.
All right. Thank you. Just a short one with the the transposing part. The intention of the transpose, is it just for the data analysis part, where you are going to take this into the data analysis so that your variables go well, or is something that is specific to NMR?
Now, what happens is when you transpose it, what you have is you have peaks on your NMR, but you can't compare the peaks statistically. So what your transposing is doing is it takes that peak, it gives it the value, and then it converts it to numerical value. So if you then look at your bins, let's say your bin from 0 to 0.4, it takes all those peaks, it takes the numerical values of those peaks and it adds it together, and it gives you one numerical value for that bin. And that is then transposed and exported to Excel sheet. So your Excel sheet that we're going to use then is going to your SIMCA, and that is statistically analyzed, the multivariate data analysis. So you need that numerical values to be able to to analyze it statistically. And that's not only for NMR. All your analysis work like that. Your GC, your LCMS, all work on the peaks, and it's then converted to a numerical value that you can analyze statistically.
I think it's okay, because it was confusing me when you compared to the text file, because I work a lot. I currently work on metabolomics on GCMS and LCMS, but then there is a text file which I thought was the one which was dealing with the conversion of the peaks into those numerical values that you then import into the either Minitab or when you do the multivariate.
Yeah, there might be your different softwares might have a different functionality, but they all work on the same principle that you need to get to numerical value of your peaks. But yeah, your different softwares might work differently. So so you'll have to check on how to get your peak values or your peaks or your peak areas or whatever they use, how to get that into a database.
Thank you, Prof. Thanks.
Okay, Shane, Dr. Mason has also just posted a definition there on transposing. So you just it's flipping over of your matrix so that it switches your rows and your column indices, right? So if they were running sort of from the top of your page going downwards, it's now flipping it so that it runs from left to right.
Yeah, I can also just mention, if you check the document that I've sent you on the Mestranova, the new Mestranova seems to be exporting it fine to Excel sheet, but if it's not giving you the bins and the values underneath that, I've added 2 steps there of how you can get your data into that. So you'll see in that document there are 2 extra steps there if your data is not already aligned to your bins. If it is, then it's fine, then you can just skip those 2 steps. But if it's not, then you can follow those extra 2 steps just to get your data according to your bins.
Okay. All right, we have another hand raised up, Prof. Kamati, please go ahead and unmute and ask your question.
Sorry, it's not a question, but I just wanted to say the document on Mestranova is, I don't think it was emailed along with the list of others, because since like maybe the document of SIMCA is the one that since like we have two documents on SIMCA, maybe one was supposed to be the Mestranova, the step-by-step document.
Oh, I see in the email, Prof, there's 2 files labeled SIMCA Basics.
Oh, okay.
All right, we'll forward it.
Okay, thanks.
Thank you.
I will send it now.
All right, thank you for that. Are there any other questions? Okay, so I think we can then move over to our break. I will request of everybody to then be back at 10:40. Welcome back, everybody. Are you able to hear me?
Yes.
Thank you. So for this session, we'll move over to the use of SIMCA, because we've now moved from pre-processing our data to having an actual data matrix that has been set up in Excel. So you'd have now copied over all of your files into one sheet. So you have a workable data matrix at this point. So now we're going to move over to SIMCA to sort of pre-process that data further and then analyze it using various statistical models. Over to you, Prof Prinsloo.
Okay, thank you, Aurelia. Yes, so once again, so SIMCA is an example of one of the software programs. It's not the only program that you can use. There are various other ones that you can use, but the principles stay the same. Many people use, for instance, R, which is fine. I mean, if you're able to use R, it's going to give you the same analysis at the end. But programs like SIMCA, and that's what we pay for, is all the calculations are happening in the background. So you push a button, and the analysis happens, but you don't have to put in all the steps of what needs to happen in that calculation. So that's sometimes a criticism on these programs as well. But for biologists and people that want to get to the interpretation of the data, we have to trust things like SIMCA, and for us it's easier to just use a program like this where all the calculations are happening in the background. You push a button and you get the results afterwards. So yes, so SIMCA is one of the examples of these softwares. I'm going to show you the different things that you can do with your data. If there are questions, like the previous session, stop and let's discuss it before we go and you lost me. In the emails that were sent, I've also sent the SIMCA basics file, which is a few steps, although it's not as detailed as the Metronova. The SIMCA is not as strict on the steps you have to follow as with Metronova. You can play around with the data and so on. So it's a guideline, but it's not as important as the Metronova. And then I've sent you the Excel sheet, so we're going to work on that one. That is specifically a data sheet that I've selected that can give you very nice results. So so you can work with me on that Excel sheet. So okay, so I'm going to share my screen. Okay, so if you open your SIMCA, we're going to start with a new regular project. And what it will ask you is to select a database. So you're going to open the one that I've sent you. Okay, and there's no data in 2 and 3, so that's fine. I'm just going to enlarge this. Okay, so now you've imported your data set. You can see there are your bins at the top, your 0.04, and it's going right up until wait, let me just see what's happening here. And it's going up until 10. Okay, and as I mentioned earlier, it's important to make sure that all your data, when you process, is going to 10. So if your data sheet is like this, then you know all your data is the same and there are no differences in the work set. So the first thing that you have to do is to select your primary IDs. So your samples, these are just numbers of samples, but you can have a more descriptive name for your samples. In this case, it's just this. What you also need to do is to select the primary ID there as well. So your bins. So these are not data. So you need this information also to be a primary ID to make sure to make your to tell the computer or the program these are the variables that you are going to look at. If you're going to do later on a secondary variable such as activity or things like that, then you're going to make use of this button here, the secondary variable ID. We're not going to do that now, but that is also available. So I'm just going to change something here to show you this database is as it is now is perfect. So it will, if you press the finish import button there, it's going to ask you to save it. But I've just made a thing here of if there are any problems on your database or on this sheet or in your worksheet, then your Simca will not allow you to save it, to continue. So if I, for instance, have the same sample name there, and I say finish import, wait, it's not supposed to do that. Oh yeah, I changed back. Let me just change it. Okay, let's see if it works now. So you see now it tells me there's a problem on the sheet, and the issues will be given here at the bottom. So it will tell you there's a primary observation ID is not unique. So you can say go to, and it will show you which one was incorrect. So if there are values that are missing or something wrong with your values here, it will also show you that. So I'm just going to change that back to 17. Okay, so this database is perfect as it is, and you say then finish import, and you can then save it on your computer, and it's going to take it into the program now. So the first thing you want to do then is you want to go to edit. Sorry, this might also be an older version. Just check on your versions that you have. That should be a similar setup, but the edit button. And the first thing we want to do is we want to look at the scaling. So there are various options. And there's a bit of a debate on this, on which ones are the best. I've done some work on this as well. The most accepted one is Pareto scaling. So you can say Control A. Just select all your samples, the variables. And set it to Pareto, and it will show here that your scaling is now Pareto. So what Pareto is doing is it gives equal importance to a big peak as well as to a small peak. You've seen on your NMR profiles, there are larger peaks and there are smaller peaks, but it's not to say that your smaller peak is less important than your larger peak. We've looked at the spin splitting patterns and so on. So your smaller peaks is not to say it's not important. And this Pareto scaling is just give equal importance to each of your peaks. If I can say like that. So most publications you will see make use of Pareto scaling. So it's important also to, in your materials and methods, indicate that you've done Pareto scaling. The second thing that we want to do is that we would like to take out the areas where your solvent peaks are. So this analysis was done with methanol water. So on the document that I've sent to you, I've indicated the regions that are link to your NMR, to your solvents. So for methanol, you're going to take out 3.28 to 3.36. And your water peak, you're going to remove the area 4.6, which is quite a large area, up to 5. If you have done the preset setting or remove the water peak in your pre-processing, then just check your analysis. If there are peaks there that are still left from your water, if not, then you can do this. But if there are some peaks left or some region that has changed now there, or your baseline is different, then it will also show as one of your differences between your samples. So we just remove the water peak. There might be peaks underneath this, yes. So this is one of the drawbacks of this method we use. But the rest of the differences we know then is because your samples are not of the solvents. So you say exclude. And one of the, no, this one is not excluded. Okay. One of the benefits here is that it's crossed out, but you can put it back. So you can just say X again and you can put it back again. So if you want to work later on your data sheet as well, you don't take anything out of your original work set. You keep your work set as it is, and you can remove NMR here, or if you want to look at observations, there are your samples. So if you want to take out your samples, you can take it out here. So you don't have to change your work set the whole time. So you use one work set, and you can just and then you can just remove your data from, or if you want to remove samples, you can remove it here. Also, if you take it out here, you say exclude, you can include it later on as well. Okay, but if you've done that, then then you say okay. The next thing it will show you now PCA unfitted. So the first thing we're going to do is a PCA, which is just it's going to give you the variation in your samples, an overview of your variation in your samples. It's unbiased. It's just you give your samples, your data, and the program is checking for the variables or your variation in your samples. It says unfitted, so you need to auto fit. And what you're going to get here is the explanation of your variation. So component 1, there are 3 components. Component 1 is explaining 21% of your variation. Component 2 is explaining another 10%, and component 3 is explaining another about 7%. So this is what you find here, and then you're going to do a scores plot. I know in some of the other newer versions, there are some options, so just do a scatter plot there. And this is what you get here. So each sample is then represented by a dot, and the scattering of your samples are based on the chemical profile of your samples. So the closer samples are, the closer they are, the more similar they are in the chemical profile, and the further they are apart, the more different they are.
Prof, I have a question in the chat for you.
Yes.
How do I know that the variable that I'm excluding is water or methanol and not a sample?
Yeah, that's now the thing. That's now one of the drawbacks of this. You will have a solvent peak, so you will have to take that out. So if there are sample peaks underneath that, you will unfortunately exclude that as well. So maybe if you use then later on a different solvent, then the solvent peak will not be in that specific region, but in this case, we will lose some of your information that's overlapping with your solvent peaks, unfortunately. Hopefully it's not too much, but you won't know.
Yes, and Mohammed, you would also have to maybe just use the literature to sort of know in which areas you expect certain metabolites. So there's a lot of published literature that says at this chemical shift you have this metabolite. So you would also need to just familiarize yourself with your sample type and where those sort of metabolites or peaks come out.
Also, later on we'll look at the interpretation, but one of the things as well, most of your compounds have more than one peak as well, which is scattered in your analysis. So if one of your peaks one of the peaks is overlapping with a solvent peak, the other peaks of that compound will probably be in other regions. So there are ways to still check your compounds. The only things that you will miss there is if it's a singlet compound with only one peak, which is underneath that solvent peak. But yeah, this is now one of the things that unfortunately that's what you have. As I say, later on, if you maybe use deuterated acetone, then you will be able to see what's underneath the water and the methanol peaks, if those same compounds have been extracted. So yeah, but that's unfortunately one of the things that you have to work around. Okay, so just to go back to this PCA, so you have two components on this axis and this axis. So you can see the samples on this axis, 42 and 66, are quite different on this axis. But if you look on this axis, they are very similar. They are more or less the same from your zero line. So depending on your two axes, you can have a look at how different they are, how similar they are, and this gives you a good idea. So this white ellipse here is your 95% confidence interval, and you can see you have some samples that are outside that. I do not like to take out samples right at the beginning, so take note of those samples that are out. It's not far out, but it might be that you just have a sample that is just that much different from the rest, especially if you work with plants. You might have a plant that chemically it's just very different from the rest. So if you take it out, you actually remove some of your information. So take note of these ones. Later on you can check. There are ways to check if it's outliers or not, but for now just take note of them. Okay, so the next thing I want to do here is to then do a OPLS-DA. And in your activity sheet that I've sent you, you will see I've given some added information on the samples. So the samples are there, and next to each of them, I've indicated what kind of activity is linked to that sample in literature. And that we're going to use now for the OPLS-DA. So the OPLS-DA, the DA stands for discriminant analysis. So it just means that you provide extra information now to your data set. So you're going to tell this program, this is my data. Additionally, use this information that I'm going to provide you and add that to your data set. So you start to work on your data set now. So you go to edit again. And if you go to observations, you will see you have an option here of classes. And we are going to group them into 5 classes, which is on the right-hand column of that first table. So you will see there's a heading for HSV, and that is samples 1, 6, 70, 21, and so on. So I've just summarized it for you. For CMV, it's 8, 36, 37, so on. So I just summarized the samples into the different groups. and you are going to put them in here. So this is going to take a bit of time. So so 1 and 6, 7, 1, 24, 9, 8, 41, 45, 49. If you highlighted them, you see their set class is 1, and just say set. And now it will put a 1 next to each of these samples that you've highlighted. Okay, so we're going to do the second group, the CMV group. So sample 8.
Prof, can I just add on here? So Prof initially did the PCA, guys. So remember, the PCA is unsupervised, meaning we didn't attach any class labels to our samples. So you just imported your samples and you ran a PCA. So your PCA doesn't know what is sick, what is healthy, or what is plant 1 versus plant 2. So moving over to your supervised methods, such as your PLSDAs, there you actually add class labels. So you are telling the software what is sick, what is healthy, what is plant 1 versus plant 2. So unsupervised, it doesn't know the class. Supervised, you actually attach a class label.
Exactly, yes. Each time, just make sure that if you put the class, just put set, and just make sure that it put the class next to it. Okay.
Prof, is there any way to remove the icon to the right of your window that shows your notifications? Thank you.
Okay. Okay, class 4. Okay, you see now, yeah, I made a mistake now. All my class 3s were now also converted to 4s. So just make sure that you don't make these mistakes. 8 and 59 should be class 3. Okay. And then the last ones should all be then class 5. So the group 5 is all the samples we've put in, samples that are non-active. So these are samples that we could not find any antiviral activity on. So these then were supposed to be then as a control. It should be separate from the rest of them, as they are not supposed to be grouped with any of the others that are linked to activity. So so they're all then going to group 5. Did I do the correct ones? 40. 1, 2. Okay. So in this case, now all of them have a class. Some people will criticize this a bit to say it's too many groups. Normally you don't want to have too many groups, because then your data or then it's difficult to distinguish the groups. The more groups you have, the more difficult it is to get differences. So then you really have to have groups that are quite distinct. If there are small differences between your groups, the more groups you have, the more unlikely it will be for your program to separate the samples. So if you have fewer groups, it's fine. This one we've worked on before, so I know that this is working well. So, and then your model type is now OPL-SDA, and that is fine because that's what we want to do now. So the moment you press that, it's going to show again it's unfitted. So you need to auto-fit it again. And it's going to give you again this, which now shows you that it's now, there's another one, 22% variation. This one is another 20%, 21% variation. So it shows you the variation contribution of each of your components. And the Q2 is the predictability. We are going to talk a bit about that later. So you're going to do a scores plot again. And if you've done everything correct up to now, then this is what you're going to find. So each class then is in a different color. And here you see what I've been talking about earlier. Some of your samples was outside the ellipse, but in this case, these are all samples with the same activity. So if you remove those samples in the beginning, you would have lost this data. So it means that these plants here are quite different from the rest, and that is linked to specific to the activity of chickenpox and influenza. So these plants that are used for those viruses have quite a distinct chemical profile. And yeah, as I say, it's amazing that this program or this, by using just the chemical information or your chemical profiles, can distinguish between plants that have similar activity. You see there are some of them that's not grouping. These ones later on we found out these were included as non-active samples. Later on there were publications which actually got activity or antiviral activity on these samples. So our model actually predicted that these samples will have antiviral activity, which was only proven later on. So that's quite nice. Okay, so this is what you have now. So I'm just quickly need to check now what are the next steps. I don't have the document open in front of me. But I think the next is, if I jump a bit around, I'm going to do them as I can remember. So the next one I think was a 3D scatter plot. So in this program, on the plot list, you see there's a scatter 3D plot. And this is just another way to visualize it. What you have here, it's on a two-dimensional, but if you do the 3D scatter plot, you get a completely different view of your information. So, and it's now in a 3D space, and there you can now see that some of your sample, you turn it around, these blue ones, you know, two-dimensional ones seemed if it was overlapping with the light blue. But now if you turn it around like this, you can see that these dark blue samples are actually quite far separated from these blue ones in a three-dimensional space. Once again, you can see these red ones are quite distinct. So this gives you a nice view of your samples, and which you cannot see if it's just on a 2D space. So there you can see these samples are quite far from your light blue. And there you can see the two that we included as controls of plants without activity, grouping very nicely with the plants with activity. So, so that was kind of predicted by this model. Okay. I think the next one there, I'm just going to go through them now. So, I just want to see where is the other.
Are there any questions at this point?
Yeah, sorry, I do not see now the screen for the chat and the questions. So if there are
No, there's no. No, there's no questions at this point, Prof.
okay.
So so while we're still at the PLSDA, you said you were going to come back to the R square and the Q square value.
Yeah. Yes.
Okay. All right.
Yeah. We'll do that a bit later on. Yeah. Okay. So permutations. So there are various models that you can use to validate your data. I talked a bit about that yesterday. So a permutation test is a nice one to use. So it takes out 100 of your data points if you're going to use a 100-point permutation, and it replaces it with random values. So if your model is then not significantly worse or not as good as a previous or your original one, then it means there's something wrong with the model, or the model is not as good as you initially thought it would be. So if you do the permutation, and you can do more than 100 permutations as well, so it's then going to take out some of the values, and as I showed yesterday, then your two lines should be quite far separated. And if they're separated, then it means that your model is validated. Okay, so there's your permutation test. So the green ones are the original ones, and the blue ones indicate the new how the new model look like, and you can see they are quite far apart. And this shows you that the model is now completely different with the permutations, and that's what you want. It means that every data point that's in your original data set is important for the clustering that you saw in your sample. So another one that you can do is this hierarchical clustering, and that is also a nice way to also check your analysis. It's a completely different kind of analysis, so it should then confirm the groupings that you find on your OPLSDA. And if you check here, that is that red group, the 7, 48, 49. In your hierarchical clustering, it's also separated. And if we'll go back to your OPLSDA, you will see it very well aligns with that clustering we saw in the OPLSDA. So that is something else that tells you that the data set is good, and what you see are real differences between your samples. Okay, then if you want to do an S-plot, which is also very valuable, I'm just going to go back here. Where was that S-plot now?
Prof, there's a question for you.
Yes.
How do we know the percentage variation explained by the axes?
Sure. I think that
is this at the PCA or the PLSDA? I think that's the principal components. Let's see. If you go to your score plots, okay?
Yeah, the summary of fit is giving you the most information on that. So, so it tells you the first component is contributing 22% of your variation, explaining 22 of your variation, 22%. So this is the best one, I think, to see which components explains how much of your variation.
Yes. And on your score plot, can you perhaps maybe just show the score plot again? I think there are also percentages listed on your PCAs usually.
Yeah, maybe on your PCA. The OPLSTA not, because it's a this is not a principal component anymore.
Yeah. Dr. Lufuno, you have your hand raised up.
Yeah, yes, sorry. I just wanted Prof to explain to them the R2X and the R2Y and Q squared.
Yeah.
Yeah, as well as the A, because the N, I'm sure everybody understands that is the number of the samples that were run or that were analyzed, but then this A and the R2Y and R2 and the Q squared.
Yeah. So, okay, these values you will use later on, and it will explain or give you an indication of how good this model is. So, the R2Y and the R2X is giving an indication of how good your model is, and how much of your variation is explained. And your Q square will give you an indication of how predictable your model is. And that means if I'm going to put a new sample in there, an unknown, let's say I put a non-active sample in there, possibility of this program or your model to accurately put it with your non-active samples is then explained by this value. So this is not very good now. You want this value around 0.4. Anything above 0.4 is a good value. But as you can see, some of your samples, some of the non-actives overlap here. So this will bring down that value. And so these two groups overlap. So this will also bring down that value. So it's not to say that if this value is low, that your model is not usable. If you look at your model here, you can see you still have very good separation, for instance, of this group. So there's some things that you can use. It just says that your model might not accurately predict an unknown sample into the correct group here.
Yes.
So that's just what those values tell you.
Prof, we have another question. So just to sum up what Prof has said, your Q squared and your R squared values will give you an indication on the predictive accuracy of your model and then the reproducibility.
Yeah.
So there's a question from Rochelle. She's asked, is it possible to do an ASCA plot using SIMCA?
An ASCA plot?
ASCA. Rochelle, did you want to maybe unmute and elaborate?
Hi there. Yes, the ASCA plot is a ANOVA simultaneous component analysis.
I don't know. I've never worked with that, so I'm not sure.
I'll do a quick Google in the background and just check whether it's doable on SIMCA.
Yeah, I'm looking around as well on Google. I think it is possible, but it's going to take a while to figure out.
Oh, so you thought Prof had used it before?
Yes.
Okay.
Yes.
No, I've never used it. It's the first time I hear of that. Sorry.
Okay. No, it's fine. Thank you very much.
Pleasure.
Okay. I just want to.
Prof, maybe if I can just ask Rachel, is it a model that is used on metabolomics data or any other data?
Yes, it's used on metabolomics data. Okay. It's kind of like an ANOVA plot, except you have a time series as well as two different groups that they plot on a similar plot to this PLSDA.
Okay. I think it has to do with what we were saying yesterday, that, you know, in as much as we're talking of NMR, there's also more advanced softwares and analytical tools that are coming up. And I think it has to be, you guys must just read. And also, we're also going to read. But I think you need more reading and maybe introduce us to those ones. I think that would be nice.
Oh, yes, definitely.
Yeah.
We usually use Metabolomics for this, but the ASCA plot that you get there it's not exactly what I'm looking for. So I'm looking for alternatives.
Okay. Yeah.
Yes.
No, sorry, I don't have an answer on that for you yet. Yeah.
Thank you.
Okay. Can I move on? Are you all happy with this ones that we've done up to now?
Did we lose anybody? Are you happy? Any questions?
Maybe another repeat, Prof, or maybe if you have another data set that you can.
Yeah, we're going to do now a pairwise, so I'm going to work further on this one to just do an S-plot, and what was the other? Going to do an S-plot here. And
the contribution plot, no?
And then the contribution plot I'm going to do on that. So I'm going to continue now on this. Okay, so let's then, why I want to only now work on groups 3 and 5 is we want to now just compare two groups so that you can get an S-plot. So the S-plot is going to give you those NMR regions which are the most, let's say, contributing the most to your separation of those two groups. So that's a very nice functionality to use to get your the regions on your NMR, which is really important. And those regions are the ones that you would like to then first focus on and try to match with peaks on your of compounds. So so that's the first thing that we want to do here. So I'm going to now just delete all the other samples that are not part of group 1 and 5, or 3 and 5. As I said earlier, you can remove them here, but you can put them in later as well. Again, you can put them back. So, so if you do this, you're not going to remove them completely from your data set. You are just going to temporarily remove them for this analysis. Okay, what you do now, you can see that I'm reducing the number of samples significantly. So, so there are now only a few samples left that we're going to analyze. So that is not always advisable. You want to have a large number of samples. And that's also important when you think about planning your experiment. That if you only need to look at one group, that there should be enough samples, because you always have natural variation between your samples. And if you have a low number of samples, it's difficult to get an idea of the natural variation between your samples. So, so in this case, there are just a few samples, but those are the only ones we have. So once again, it will now show it's unfitted. You're going to auto fit, and what you see here is that you immediately get a better profile here. So your components, this one explains 77% of your variation. This one adds another 13–14% and so on. So your variation here is almost 100% explained, and your Q-square values are immediately increased significantly.
Prof, we have a question.
Yes.
Is there reason to just use class 3 and 5 for the S-plot? I think you explained that that model requires two groups.
Two groups, yeah. So you can use any of the groups. I just selected those two now because we know it's quite different, those groups. But if you work on your samples, you're going to probably investigate all of them. If you have more than two groups, you're going to take out one group, compare two, put it back, compare other two. So that's where you have to start now to look at your data and see where you can find your differences in your samples. So yes, so this was now a decision from my side to just use 3 and 5 because I specifically want to do an S-plot.
Prof, I'm also seeing something that I don't know if the others are seeing. As you had alluded that Q2 must have at least a 0.4. And I see that's where it is now on this one. After you've removed some of the data sets, it's now on 0.4.
Yes. So, and you will see now, if I do the score plot, you can see why.
Yeah.
So previously, in the previous score plot, we had some groups overlapping. And for instance, the non-active, some of the non-actives were overlapping with some of the others. And that brought down that predictability or predictive value. In this case, these two groups are so distinct that if I put an unknown sample in here, it will almost, with 74% accuracy, put it in the correct group. So you can also see those samples that was grouping with some of the other antiviral samples are now with the non-actives, which means that that chemical profile is not similar to any of these. So even though it was similar to some of the other plants with antiviral activity, it's not the same as this group here of the chickenpox and the influenza antiviral activity. So now it's more similar to the non-actives. And so now you can see R2's your R2 values are now very high because it explains a lot of your variation. It's now a good model, and your predictability has increased quite significantly. Okay, so then we can then do an S-plot. You can see now it's possible to use it. If you have more than two groups, you cannot use the S-plot. And this now gives you samples on this side, NMR regions, which is contributing to your one group, and these ones that are contributing to the other group. And now you can see some of them are really important, really quite far from the others, and those. And these ones in the middle, they are kind of the ones that are more or less similar between your two samples. So, and that you will find, because you have primary metabolites that needs to be in all your plants or in all your samples, or you have a base of compounds that you will find in both, and the NMR regions that are linked to those compounds you will find here. So these are probably less important, and these ones here are the ones that you will now start to investigate further and look into more detail and try to match with peaks of compounds. Okay, so this is a nice feature.
Prof, can I just interrupt there? So if we look at 3.64 1.4, remember these are regions, right?
Yeah. Yes.
So if you guys remember, we did binning, so we chopped up our spectra into segments, or we've sliced up our bread and we have those different slices. So now this is saying region or slice 3.64 is mostly different to the rest of what is there. And so you can now go back to your raw spectra or your raw data and go and sort of zoom into that region and go and look further for what exactly in that region is causing these differences.
Yeah, and that's quite important. You will do all these kind of plots, but at the end you have to go back to your original data and go and make sure that what you see here is actually a true reflection of what you see in your analysis. So and also, I mean, this is the bin at 3.64. So your peaks that are different might be a little bit to the left or a little bit to the right. So it might be, let's say, 3.61. So you have to give that bit of leeway as well when you go back to analysis to just consider that it was the bin. So all the peaks next to that in that region is in that bin. So it might have a slight variation on 3.64 and not exactly 3.64. Yes.
Yes, exactly. So it's just that region. Yeah. We have another question for you, Prof. Do you perhaps have references that state what the acceptable R square and Q square values are?
As I say, the Q square is normally around 0.4, but as I say, it's a value, but it's not cast in stone, because as you see now, when we do the pairwise comparison just between your two samples, now we have a 0.7. So it's not to say that just your model is not good. It's just telling us in that specific plot that you have, the predictability will not be as good if you put an unknown sample in there. So 0.4 is more or less the acceptable thing there. The R square, I don't know. Normally your R square is quite good, but I think it's around 0.7 or something. Really, I don't know if you. I cannot know exactly.
If I remember correct, I don't know if Dr. Mason is here, but it should be closest to the closer it is to 1, right?
Yeah, the better, yes.
The better.
So I think around above 0.7 is normally accepted as good. But these are just indicators, so just keep that in mind, especially if you work with samples. For instance, this model, we've worked with plants of different genera. It's not even plants that are similar at all. So you will expect that there will be a lot of variation. So just keep that in the back of your mind. If you work with serum samples or blood samples, you expect it to be a bit more similar. Or if it's from people that you expect the samples to be similar, more similar, then you will look more at those values. But just keep in mind, if you have samples that are very different, that those values might drop a bit. Okay, so on this, let's also just have a look at the hierarchical cluster analysis. And if this is such a good model, then you will see it here again, and this is exactly what you see here. Your 3 samples of chickenpox influenza, again separated from the rest of the samples here. And just note here that sometimes when you have more than one group here, 59 is not the closest to 51, because 59 can be on that side as well. So it's not to say that these two now are close. So just keep in mind that these are groups, and this is a group. So so it's not that these two now are close to each other, or similar, or have a lot of things in common. Okay. Okay, let me just check if I've now. It's just a contribution plot, I think. Yes. So let's just do the contribution plot, because that will link up also with what we're going to discuss afterwards. Not there. So now I can't remember where I normally get the contribution plot. Is it this one? Let's just see. Yeah, okay. So there's your contribution plot. So again, these are your bins at the bottom. So it goes from 0 to 10. So those is similar to your NMR regions on your profile, but again, that value there is for that bin. It's not for a specific peak in that bin. And now you can see which bins are important here. So the ones at the top is the ones that are contributing to the separation of these groups. So if it's to the top, it means it's positively associated with that group. And if it's to the bottom, it's negatively associated. So for instance, this peak or this bin here at 1.4. So it's showing you that it's a large peak there. So So you will probably have a big difference between your samples there. This does not mean that it's now a, it might be that there is a peak present that was not present in the other sample, or it can just be an indication of a decrease or increase of concentration or the height of your peak. So it's not to say something disappeared or appeared here. It might be just an indication of the concentration as well. Remember, we've Pareto scaled your data, so each of your peaks will be equal in importance. So, but now this bins tell you these are the bins that you have to go and look at, because these are probably the areas which are linked to a compound or compounds with peaks in these regions. And if it's true, you will clearly see that now on your NMR analysis. So I just want to go back here to the scatter plot. Another way of doing that is to circle your samples and then to do a contribution plot there. And that now shows you for that sample, these ones are positively associated and these strong ones are negatively associated. So these ones are associated with the samples or the red samples. And if you're going to switch it around, if you're going to highlight these ones now, you should more or less get an opposite view of your contribution plot. So these ones tell you then, these are important NMR regions responsible for those 3 samples moving to the left or clustering separate from the blue samples. Okay. Any questions?
I think this is the exciting part of NMR, where you can actually see the separation of the positive versus the negative. And I always say the ones below, that's how I used to explain my data. I'll be like, the ones below are the negative ones, or as Prof said, representing this kind of maybe data. And then the one above are like maybe the positive ones, and it was easier that way. And from, yeah, okay, sorry. I'm getting carried away, I'm getting excited.
I don't see any questions posted in the chat, Prof.
Okay.
Does that mean everybody is still following? Can I have thumbs up, perhaps?
Prof, before you continue, there's one who posted on the chat, I don't know if you saw it, that an article that is talking more of the Q2.
Yes, I posted the article on the chat.
Okay. So,
okay, it seems most people are following, Prof. I get a lot of thumbs up. Somebody has their hand up. Let me just see. Go ahead and unmute.
All right, thank you once again.
Yes.
Yeah, I'm looking at this, the current one here. Can you, Prof, relate it to the previous, what was that? The one you showed is the 95% confidence, or that one which was where you had the outliers that you said we need to take note of. I want if this can be related to that, so that we can explain, maybe can give us an understanding on those which were kind of becoming significant.
Yeah, you see, yeah, if we just, I don't think I have that. Let's go to this document here. Sorry, you can see my computer is a bit old. It's taking quite a bit of time to just open one document. Sorry. I just want to show you those, just want to go back to these, to what we've seen here. Okay, so yeah, so that was a regional school plot, or this was actually a regional one. Oh, I don't have a PCA there, but yeah, these ones the whole time was outside that 95% confidence interval. So it just says that these samples are quite distinct. If it was, for instance, a sample, let's say you're working with one plant and they were just treated differently, let's say summer and winter, and you have winter samples that are all like the yellow ones, and you have one winter sample that's out there, then it will raise a flag to me to say that is probably something wrong with either your sample preparation. It can be like that. It can be that one of your samples was not handled the same, or your grinding was different, or there was a difference in you probably did not pipette properly, or something along the lines, or your NMR analysis is not good. That's often the reason. If you go to that sample, you will see that the resolution is not 100% or something like that. Then you have a sample that's like these ones outside. But when I look at these ones, these are 3 that belongs to the same group. So it's outside the 95% confidence interval, but because it's from the same group, I think I would not exclude them, because it just means they are so much different. But it's not to say, I don't regard them as outliers. I just regard them as completely different from the rest of the samples. You can go and check these samples. Maybe it was also samples that was run one right after the other, and the resolution was not good, and that's just by mistake, or that they all are in the same group. So when something is outside this confidence interval, you will go and check those samples out. And make sure that it is not something that was introduced by your sample analysis, sample preparation, or with the analysis on the NMR. If it looks fine, then I'm very reluctant to take samples out. And when we've done now the S-plot or the pairwise comparison, you can now see it's inside the 95% confidence interval. So when you only compare these groups, it's not showing that they are that wildly different. They are separating, but it shows that it's okay. If you just compare these two, they're still inside the 95% confidence interval, and I'm happy. I won't be concerned about these samples.
Does that answer your question, Dolo?
Yeah, I think it does. It's okay.
Prof, maybe if you can just, like briefly explain when is the right time to remove the outliers, or what would make certain that these ones are outliers, perhaps, just so that they can understand.
Yeah, so let me show you these ones. They're Tellings T2 and the D model X. You can use that to check your samples. So for instance, if you do this, it shows you in the previous one, one of those will probably be out here or out there. So it will show you these are different models that's checking for outliers. If it's not an outlier in both of these, I won't remove. But also, once again, just make sure first that there's not something wrong with the sample. If you go and check the NMR analysis and you see the resolution is bad, then you don't even need this. Then you know immediately it's an outlier because of the analysis that was not done properly, or your pre-processing was not done correctly. Maybe something like your normalization. You've done it on the largest peak or not on your TSP, or you forgot to do baseline correction. So things like that. But that you will immediately see if you look at your sample. If there's no problems with that, then you can use these two and check if in both models they are outside the 95% confidence interval, and then you can regard them as an outlier. But as I say, you will see immediately on the sample itself if it's really a sample that should not belong in your database. And also, I mean, I mentioned now that I don't like to take out outliers, but if you don't take out outliers, it will sometimes hugely affect your clustering of the rest of the samples. Because if that sample or samples are so different from the rest, then it cluster your outliers as one group, and the rest of your samples is another group. So now you have two separated groups because your outliers are so different. And if you don't remove them, you won't see the differences in the rest of your samples. So if you remove those outliers, then sometimes immediately you then see a separation on the rest of your samples. And that will also give you an indication that those samples that you took out was real outliers, because it really affected your clustering or your visualization of your differences between the rest of your samples. So, and as I say, you can put it back also. If you take out the outlier and it doesn't really affect anything, you can always put it back if you think it is an important sample. So it's not as if it's gone forever, but just be careful by not taking out samples just left, right, and center. Be careful when you take out samples, because it means you are now changing your data set. So if you take out samples, there must be a reason for that.
Yes,
and also,
thank you.
Sorry. Sorry, Doc. And also that's why it's important when you're preparing your samples, you make them in duplicates or triplicates, so that when it happens that you have to remove some outliers, you don't end up removing a sample, because that will cause maybe biasness when you no longer have other samples. When you remove one sample and then it's already gone, at least if it's double or triple when you're preparing your NMR samples.
Yeah, thanks. That's a good point. Yes. So if you have 3 reps, technical reps of a sample, or even if it's not technical, if it's just sample reps, the same sample that you analyze 3 times, or from the same batch, one batch you take 3 samples and you analyze them, then you expect them to be more or less in the same region. If you have 2 that's close together and 1 that's an outlier, then you know there's something wrong with that sample. So yes, this brings us back to experimental layout, and before you start your analysis or your experiment, to make sure that you have enough samples, and also that you include your replicates, because that gives you a lot of information, and especially on your control samples. We've seen often that if you do not include reps on your controls, and there's a problem with your control, or your analysis was not good in your control, then that sample is lost. So it's good to have replicates, and then if there's a problem with one of your samples, you can take that out, but you don't lose that sample completely from your analysis. That's right. Yeah, thanks.
So I think that the take-home message with that is, a lot of times with metabolomics, individuals want to force the samples to separate.
Yeah.
And you shouldn't do that, because you might actually be forcing something that isn't there. For example, Prof showed us the 2 samples that actually had HSV activity, right? And had he just taken out those samples and said, okay, well, I know these are supposed to serve as controls, let me just take them out. But those samples actually clustered with the control samples, actually some of those that they regarded to be controls actually clustered with the samples that actually had medicinal value. So they then went back to look at why those 2 samples clustered with the others. So your removal of outliers should be based on your biology, and then it should be informed by your statistical models. So in the case of sick patients, for example, we know that with some diseases, you would have sort of uninfected control, and then you'll have someone that is mildly sick and then someone that is severely sick. So sometimes the ones that are mildly sick will sort of overlap with people that are sort of uninfected. But remember, the uninfected group might have other underlying issues that they don't know of. So it then makes sense that a mildly sick group will sort of overlap slightly with a group that is uninfected in that case. So keep the biology in mind and interpret your data in that sense. Don't just try to force things to separate.
Yeah, that's very important. And thanks for this. Yeah, so this was a good example, for instance. So those two samples were included as non-actives, as controls, and they grouped now with the active ones. So if I took those out because I wanted to have a nicer picture, I would have lost that information of when we later on realized that these plants now have activity published on them as antivirals. So don't force and that's the whole thing of removing samples. Those two are not clustering with the rest of the samples. It brings down the Q2 value, but as I said, I'm not too concerned about it because I can still get a lot of data from this set. By removing these two to have a clearer picture is going to actually remove a lot of information for myself. So don't force your model. This is what you get, and first try to see why these samples are on this
clustering that way,
or an outlier, before just saying I want to have a nice picture and I want to show everyone that my things are so nicely clustered, and if they group where I want them to be, I'm going to take them out, because then you're forcing, and then you probably then will not get proper or an accurate analysis or interpretation from your data. So be careful, just be very careful on that.
Sure, Prof. And I think that's where we talk of cooking of data, you know.
Yes.
Obviously, you are trying to cook data and so that it can make sense to you. The problem there is when you are publishing in journals where they require raw data. Okay, then you're going to have a problem because they're going to say, "What? But we're seeing these. What about these other ones? What happened?" Because in as much as you are going to be removing the outliers, you cannot remove it from the raw data. So that's going to be a problem.
Yeah, and as I mentioned in those videos on Tuesday, what we've seen with this metabolomics is that we often find results that are not conforming to the general beliefs. So if you think that this is how it should be because literature is saying your samples should be separated like this, and it's not, you might just be losing out on important information that is actually right in front of you, but because you want to conform to a certain belief or a expectation, you're going to force it into a different way, and then you lose information that is valuable. So it's not to say that you have to find results that are mainstream or that other people have found before. You might maybe see something here that's not been discovered before, and that's why it's different to what you expect.
Yeah. I have a final question here, Prof. I see we are at 11:54. I know you're still discussing the current plot, but Francis seems to, Francis' question is, as we get to know the contribution, what about the specific metabolites, or did I miss this part yesterday of the data from NMR? I don't think you've missed anything, Francis. We're showing now how you go from the raw data, and what we did with that data is we chopped it up into bins or segments, and we are now looking for where in those regions are the differences. So I think Francis's question relates to wanting to see the names of the metabolites now. So what is it that's important?
Yeah, so we'll get there. I will try to touch on that. That's not that easy, and it's a long process. But the last session, I will touch on that. These are your important NMR regions. Now you try to match them on the databases, for instance, and try to get to a name of that compound and see if it matched or not. So that will be the next step. You got your contribution plot, you see the NMR regions that are of importance, and now you want to relate that to a compound or compounds. Yeah, that's I tried to highlight a bit on that in the last session.
Prof, one last question, Prof. Williams, if you can allow me, before we close or go for break. Prof, between the two modules that you have shown, the PCA and the OPLSDA, which one would you say is highly preferred, or is there between the two, is there any that is better than the other?
See, the PCA, I've got feedback often from where we use OPLSDA and people say you should not even use that. But because your PCA is unsupervised, it's non-biased, so that's the data you have. It's putting it in the program, and it's showing the variation in your samples. So the PCA is the most, let's say pure analysis of what you can get. But if you work with plants that are, or samples that are, where you have a lot of variation between your samples, then PCA might not be good enough, and you might have to add more information. For instance, in this example that we use now, the PCA was not very good. There was some separation, but it was not exceptionally good. Only when we started to do OPLSDA, we started, for instance, this red group, those three samples grouped together on the side. So there's value in both of them, but I don't think the one is more important than the others. It will also depend on your project. But I think, really, maybe in your case, where you work with samples, maybe that's more uniform, a PCA might maybe be giving more separation.
So in our case, Prof, we mostly use we tend to use both, so we don't give priority to one or the other. So the PCA, we usually, as you said, that gives you the raw picture of your data. How does this look naturally without us adding a label? So that just gives you that natural variation or the natural clustering profile of those samples that you have run. But of course, because the supervised methods, you've told it which group of samples belongs to which class, right? So I have sick versus healthy. So the supervised is then more for trying to pinpoint those markers that differentiates those groups.
Yeah.
Whereas the PCA is then just for the natural clustering and, commenting about the homogeneity of your sample groups and stuff like that. But the supervised methods is then mainly for, okay, they separate out, but what is causing the separation?
Yeah.
So I guess what is important here to take is that you can rather change the model or rather move to another model, but not mess up with your data. Don't touch your data, but maybe just move from one model to another, or use both.
Yeah, you see the one is supervised. Yeah.
Yeah, so you're gonna supervise but not removing your data and all that. I think okay.
Yeah, there's a difference between changing your model to fit something and supervise or guide your model. For instance, adding the groups, there's a difference there. So with a supervised model, you provide extra information to your data set to say, add this information as well. You are not changing your model. Whereas if you take out samples and so on, then you are modifying the sample set. That's two different things.
So I always say use it, whatever you choose should complement one another. It shouldn't be to cancel out the one or try to fit or change anything in the other one. Your PCA should be complementary to your PLSDA. All of them should fit and tell the same story in support of whatever it is that you're trying to show.
Yes.
Okay.
Okay.
Prof Prinsloo, were you done or are you still continuing?
I'm done on this. The last one is just the interpretation of the data, but on
Okay.
this SIMCA we're done.
Okay. I don't see any other questions. So I do think it is 12 o'clock right now. I'll give a 20-minute break. So then in the next session, we'll do interpretation of the results and then move into the discussion as well. Is everybody okay with a 20-minute break? It's exactly 12 o'clock, so we return at 12:20.
Yes.
Okay. Again, you can stay logged in, and then I'll see everybody at 12:20. So I'll hand over to Prof Prinsloo, who will deal then with the interpretation of some of your metabolomics data.
Okay. Okay, good. So I'm going to try to touch here on as much as possible here. So if there are questions, I think let's might discuss that then. But once you have your data, your SIMCA analysis, then you have to start working on the data and the interpretation of that. And I'm going to show a few pointers of where you can start and what you can do. But each project will be different. So so there's no guaranteed method that will work for you, or that this will give you all the answers. But it is important to take your data and start working on that and see how much you can mine from that data. Okay, so you've seen now what the analysis looks like. So this is a typical NMR analysis of a extract. This is a plant extract, Sutherlandia. And just an example, you can see here's your TSP peak. So once again, linking to the discussion this morning, your TSP peak will be quite distinct, around 0.0. If it's not that, then you can just put it exactly at 0.0, but your TSP peak should be like this. It should not be so small that you can't distinguish it from the other peaks. Also, maybe on that, you can also check if you're not 100% sure, if you have a water peak, if your water peak is at 5, if it's a bit shifted, then you know where to look for your TSP peak. Also, your methanol peak is around a 3.2, so that's one there. So so if your peaks shifted, then you can get an idea of where you are in your profile by looking at your water peak or your TSP of your methanol, or if you have chloroform, which will be at 7.2. Okay, so so this is more or less what you have. We talk about the aliphatic, your sugar region, and the aromatic region. So aliphatic region is more or less from 0 to about 2 or 2.5. And this is mostly where you have your single bonds, carbon, hydrogens, or single bonds with double bonds. Your sugar region, where you have a lot of oxygens and OH groups. And sometimes also some of your others, like your nitrogen or so. And then in this region is your aromatic, from about 6 to around 8 or so. Is your aromatic. So if someone talk about these regions, that is what they are referring to. So I'm just showing this now again, so that you can see this is a good analysis. The resolution is good. If you will zoom into these peaks, you will see that they are really well defined. Where there are duplets or triplets, you will see that they are doublets or triplets. You'll see they are well resolved. So this is a nice analysis. And of Sutherlandia, I'm going to show you now one that is not a good analysis. So this one is also of Sutherlandia, but you can see the quality is really not good, the resolution. And this one was run in between some of the other samples. So just to come back about the batch processing of this morning, if you have this one in between, you will process this the same as the others, and you won't see this analysis. No, it's not good. So yes, obviously, if you have thousands of samples, one or two bad samples will not have an effect. But if you have like 80 or 100 or 200 samples, things like this will affect your analysis. So immediately you can see the resolution is not good. And I just put them here next to each other so that you can see it's more or less the same kind of peaks that you see here. So at 3.5, you see those ones. You can see the profile, everything looks different. And on this side, here, 8 and 7, the peaks are there. So it's not as if they are not there. The quality is just not good. And if you put these two into the same database, this one will probably be an outlier. As I said, first go and check your analysis or your sample before you take samples out, because this is a clear indication that this one should not be in your sample group. Okay, so that's one thing. But also, maybe just before I go, you can see this TSP peak. In this case, it's the largest one. So this is what your TSP peak should look like. It should not be that small that you can't see it. So you will easily be identifying your TSP peak in one of your samples. So if you look at this, for this sample, as an example, the sugar region here is, I will talk a bit about that. I've talked about the aromatics, anomeric proton, identification of sugars in NMR. So here you see your sugar region, and you can see this sample is quite rich in sugars, a lot of peaks here. Also aliphatic compounds, but also a lot of sugars. And for instance, these are quite interesting, so I'm just going to use this as an example. You do not often have peaks this far downfield. Normally around 7.5, maybe 8 or 8.2 or so, but you really go down to 9. So these peaks were quite interesting to us when we had a look at this sample, because they are so far downfield, and they're quite distinct. If we enlarge, I will show you the enlargement. So they're quite nice to have a look at. So because it's not in a region where you normally find a lot of compounds, we had an idea that it could be something with a nitrogen aromatic region with aromatic ring with nitrogen or something like that. And then we started searching for samples that or compounds that might be absorbing in this region this far downfield. And we came upon this one, which is trigonelline. And you can see there, this one has got peaks at around 9 and 8 and so on, which was a possible good match with those peaks. So we need to put it on top. So this, for instance, this is from the Human Metabolome database. So if you go to Human Metabolome database, if you click on spectra, so for trigonelline, there is a NMR, proton NMR spectra. And then you can see how the peaks look like of the pure compound. And you can see the peaks, the peak ppm values match very well. Also, what you want to look at if you're going to start to match compounds is the peak shape or the splitting pattern, as well as the height of the peaks. Because a compound will always have the same pattern, the same splitting pattern. It should always be at the same place. The ppm value should be always the same. So you can't have all of a sudden a huge peak here and then a small one here. Then you're probably looking at a different compound. So the whole picture of a compound will give you an idea if you are looking at the right thing or not. So in this case, there it seems like a singlet which match well. That looks like a few peaks that match well there. But here, it looks a bit different. So, so we had to investigate a bit further there. So this is a screenshot of Kenomics. So Kenomics is also a tool that you can use. Kenomics make use of the information in the Human Metabolome Database. So this is also the trial version. It's a bit expensive to buy this program, so we make use of the trial version. What happens in Kenomics is you can upload your sample, and then you can match it with compounds in the database. So for instance, here we selected trigonelline, and the blue peaks are the peaks of pure compound trigonelline, and the black one is our sample. So this is the exact same sample that I showed you now in the previous slide. And there you can see, now you can see it match almost perfectly. So you have a nice singlet, the shape is the same. Here you have a doublet of doublets, 2 doublets, well matching these ones. And that one that was kind of strange in the previous one, you can see there are the peaks. These are peaks from another compound. So if we go back, so those peaks are the ones here at the bottom. So these huge ones here that was confusing us does actually not belong to trigonelline. So those ones are from trigonelline, and those ones are from a different compound. So for trigonelline, you have your peaks here as well as the one at 4.4. If these doublets were not here, then it's not trigonelline. If that singlet was not there, if you have this peak and that peak, but this one is not here, then it's not trigonelline. Then it's maybe something similar, but it's not that peak, not that compound. So if you look at a compound like trigonelline, all the peaks must be present, and all the peaks must match the splitting pattern or the shape of your peaks. You can sometimes, even with a singlet, sometimes it's a broader singlet or so, and then you can quickly see if it match or not. If it doesn't match, then you will probably look at the others, and if one is not matching, then the others will probably also not match. What you will see here is the blue is the regional ppm value, and the red is where our peak is. You can see it's slightly moved, and this you can find in extracts. Kenomics and the Human Metabolome Database provide you the profiles of a pure compound. It might also be at yes.
A question here. So most databases that have the pure compounds listed, those are usually at physiological pH closer to 7.4, right? Mm-hmm. Could that small shift be because your work is done at a pH of 6?
Yes, yeah, exactly. So that was my next sentence. It can be, yeah, so it might be that you have interaction or that environment of your compound is a bit different in an extract or the pH. So that slight difference in your pH might result in that one slightly moving to there. But you can't have this peak now at 8.2. So you will have a slight maybe shift in a peak, but it won't move that much. And what you often see is that all your peaks will then slightly move.
Okay.
So if you see peaks that are matching, but maybe this one is just here, then this one, all of them will be sometimes just slightly moved. So that will also give you an idea. Once again, all your peaks must be present. So if for instance, only that peak was now not there, but all the others are matching, then you can say, okay, well, it's probably because of either the extract or the pH, and I'm quite confident that this is the peaks that belongs to this one.
Okay. While we're here, Prof, since you have so many representative peaks, you said earlier that sometimes a peak might be masked by a very large peak, right, by something else.
Yeah.
But that you can then use one of the other peaks related to that compound to actually do the quantification. So this is an example just showing you guys that you find for trigonelline, you have these different peaks at the different chemical shifts or different positions. So let's say your peak at 8.1 was completely masked. You could then use the peak at 9.1 to sort of quantify. And how does the quantification relate, Prof? Whether you use the peak at 4.4, 8.1, 8.9, or 9.1, should that quantification be similar?
Yes, you will see if you work in kinematics, if you move one peak up, all of them move up. So this will also move up, and that's why I also said it's important to check the heights of the peak, the shapes of the peak, and the splitting patterns, because if this one is this height, these doublets cannot be this high, because then it's probably something else, or it's overlapping. It might be underneath, but it's overlapping. So then you won't use this for quantification. You will use the one that's resolved. And in this case, you have 4 peaks. So if, for instance, this one was overlapping, then you had 3 other options to use. This one, obviously the easiest one, because it's the best. It's just a singlet, so it's easy to match the height. But yes, if there's an overlap of some of your peaks, then you will use some of the others, and just check that let's say the profile of your compound looks similar to your original one. As I say, if this was very high, then you can also not use this for quantification, because it doesn't match your pure compounds.
Yeah. Then there's a question from Ovia in the chat, Kamati. Does it then mean it's preferable to adjust the pH closer to 7 or to physiological pH?
Yes, you can, but it doesn't really make such a huge difference. So we sometimes have a bit of a movement, but I haven't not seen really where it shifts completely.
Completely, yeah. So the shift, Kamati, just should not be that significant in terms of your pH change. So if your experiment has been optimized to a pH of 6, yeah, I mean, those, as you can see on this picture, the shift is very, very small.
And also, before I would then move to a new pH, I would rather then go and check LCMS or another analytical technique to see if I don't find that compound there. So that will be a much better confirmation than just to change the pH. Or take a standard. You can buy trigonelline and add it to your sample and spike it and see if those peaks increase. So before I start to play around with the pH, I would rather go and find another way of confirming that I am looking at trigonelline.
Okay.
Prof, maybe if I just need to add that this is the most strenuous stage where you have to annotate the compounds. Believe you me, you can go for days not getting anything. So you just need to be patient, and just be patient and patient and patient at all times until you get it right. And so whenever because what usually happens with Chronomics, if it's you see the one that's turning green, once it matches the peak, it will definitely change into green. And then the minute you try to move it to another one, it will either deactivate the color and be, there won't be a color or something. But once, if it's perfect match, you'll see the color also changing. So you just need to, and then maybe have a book where you can write the peaks where they are found, the NMR regions, and all of that on the side, so that you can always compare. But it needs time. It's not something that you do today and you can just conclude tomorrow or the very same day.
That's very true, yes. And also, I mean, when you start working with your samples, you'll get used to your samples. So you'll kind of start to know that these peaks now belong to trigonelline. So if you find now another compound with peaks in this region, you'll be very skeptical to annotate it to another compound because this one is here and this one is present. So you start to know your sample and to know where the peaks are, and you'll start to identify peaks that are strange from your other samples once you start to working with them. So going from just a bunch of peaks to going to annotation takes a bit of time and takes a bit of energy and search in literature to make sure that what you are looking for is a probable match. This is not identification yet. This is only on the level of annotation. A most probable compound matching to these. You either have to then isolate, identify, or you have to spike it with a pure compound, or then go to LCMS or another technique to confirm that it's in the sample. Then you can only say to identify. Okay. So the other region that I was talking about is the sugars. As I said, with NMR you can have a lot of information on your sugars, and this is, for instance, the human metabolome database profile for sucrose. And you can see there's a peak at 5.4, nicely resolved doublet, and then in the sugar region, 3 and 4, you have a lot of peaks. So this one we call the anomeric proton. That is a very nicely isolated hydrogen, which normally absorb around 5 or 5.4 or around 4. So they are in a region where you don't have a lot of peaks. So this anomeric proton can be used very successfully to identify your sugars or to annotate your sugars. And so sucrose gives you this doublet here. Once again, you're going to check that in your sample you also have a doublet. You're going to check the peak shape, and you see it's a very sharp, straight doublet. It's not a broad one. So if you have this broad doublet, even if it's at the same place, it's probably not the same one. Because with sugar, it's difficult to match all these. In your sugar region, I'm just going to go back. You can see there are many peaks here. Because if you have 2 or 3 sugars, all the peaks will overlap here. So the anomeric proton is easy to use. And sometimes you can also match the profile of your sugars here, but it's not that easy. So these are the ones that you're going to focus on. So the one here at the bottom is, again, in Kenomics. And there you can see the peak, the blue peak is of pure sucrose, and the black one at the back is of the sample. And you can see the shape is almost exactly, and it's exactly at the same place. You can see that's where it was originally. So this is quite not a definite, but a good chance of having sucrose in your sample. And once again, you will just then confirm. You can maybe add sucrose. That's easy to buy, so you can spike it. And if you add pure sucrose and this peak increase, then you have sucrose. So, but this gives you an example of your sugars in your sample. There's another one, a doublet. You see it's slightly overlapping with others, but this one is probably trigonelline, which has got a peak at around 5.18. So you see there are not many peaks overlapping here, and that's why it's a good region to check for these anomeric protons of the sugars. So if you check then, if you look at this sample, you already can see that you have trigonelline here, and if you use that peak of sucrose, you'll know that many of these peaks here already contribute or can be assigned to sucrose. There's probably 1 or 2 other sugars there in as well, but you can already write down sucrose because you probably will have sucrose in your sample. Any questions up to here?
Yes, Prof, I just want you to maybe explain to them the difference, because this is one of the things that we used to, it used to confuse me, the difference between the singlet and the duplet. Can you please just explain to them whether, having a duplet peak means what it means, or yeah.
Yeah.
That.
Yeah. So that I've highlighted and emphasized quite a bit yesterday in the presentation, and that's a reason why I highlighted that yesterday. That you distinguish between your shift, where it is on your scale, and the splitting pattern. So if you look at the others, that's also a doublet, and there's a triplet. So those are not 3 peaks, it's a triplet. And if you're going to try to match it on your peaks in that region, there should be a triplet. That's what I say. And it's also maybe slightly separated from the rest. So you should have a triplet as well in that region. But the splitting patterns, for those of you, that's just a refresher of yesterday. So if there's a hydrogen next to the hydrogen, this is a peak for a hydrogen. If there's a hydrogen close by, 2 or 3 bonds away, then it will have a splitting pattern. Then it will make a doublet and not only a singlet. If it's a singlet, it means it's a hydrogen without any hydrogens around it. When it's a doublet, there's 1. If there's a triplet, it means there are 2 hydrogens next to it that will influence the splitting pattern. And this you often see with sugars because it's your ring structure and you have a lot of hydrogens on that ring. So you have the splitting patterns with your sugar. But you can just revise yesterday's presentation on the splitting patterns if you're not sure about what you see here. Okay, so getting to a bit into interpretation of samples. So this is an example of helichrysum. That's also a well-known plant in South Africa that many people know by Impepu. So if you just look at the profile, you can see there's the TSP again. Once again, it's a strong peak. You will definitely identify your TSP peak. It will not be hidden between your other peaks. This is quite easy to identify. If you look at this profile, you can see there are not many peaks in the aliphatic region. There's almost none. These are probably amino acids. You have a bit of sugars. And then you have a few peaks here in the aromatic region. But mostly your sugars, this is your water peak, so residual water. So mostly your sample is dominated here by sugars. And you can once again immediately see, I think that is already, you can probably think this is sucrose. It's at 5.4. And if you enlarge, you will probably see it's a doublet, which will match the doublet shape and the size of that. So this you can immediately say there's probably sucrose in your sample. So some of these peaks probably belong to sucrose already. There's maybe another aromatic proton. So maybe 2 sugars that you can see at this stage. So this sample, so we've collected quite a few of these samples in different areas. So this is also Helichrysum aureolitens, the same plant. Let's say about 2 or 3 kilometers apart. So it was not even far from each other. So if you look at the analysis, again, you see your TSP peak, nicely resolved. No question about if it's TSP. But here you can see definitely more of your aliphatics. You have sugars, but it's not as pronounced in the previous one. But look at this region. Very strong aromatic peaks, almost higher than your sugars. So same plant, same species. And the only difference that we could see here, they look the same, exactly the same. There's no difference when you look at them from the outside. The only difference is that the one was growing in a drier area, and the other one was almost like in a marshy area where it's wetter. So, so the environment of this plant had a huge effect on the chemical profile. So we have a study that we've investigated this further, but in your Mestranova, you have a functionality where you can either stack like this, or you can superimpose like this one. So I will show you a bit more of what we can do here. And this is very nice to compare your samples. Important is that you have to reference at your TSP peaks to make sure that they are both at 0. So to make sure that all your other peaks are aligned. And then you can compare the regions like this. So you can see these compounds are probably there, but it's much lower. Sugar profile look very similar, except that in this case it's much lower. So so there it's more pronounced, your sugars, here it's less, and then here it seems like the peaks are there, but in such low concentrations that you almost cannot even pick it up. So and this also shows you the value of making sure, recording where you collect your samples. Make sure that, as I mentioned many times now, is make sure your handling of your samples are the same. If these samples were handled differently or stored differently or dried or something differently, then you would not know if this is the difference that you see here is because of handling, your handling areas, or if it's really of the samples. So in this case, we know these are a true reflection of the chemical profiles, because they will handle the same. Extra care and precautions taken when all the samples were processed. So when we see this, we are quite sure that what we see there is real differences reflecting the chemical profile of the plants in the field. So we went afterwards and collected samples again to confirm, and we got the same. So this is the value in, at the end, be able to trust your analysis. Even though it's the same plant, it looks completely different, but it's not because you made a mistake somewhere. You know that this is a true reflection of your chemistry in the plant. So obviously, we wanted to have a look into those ones, because those are in the aromatic region. I mentioned also that many of your flavonoids are absorbing in that region, which contributes a lot to your activity. They are very biologically active compounds. And also what is important at this stage is to go and have a look at literature to find out which compounds have been previously isolated in your plant. So if there are compounds that are quite abundant in these species or in this genus, then go and find the NMR profile and match them. So this is also a start where you can start to find out which compounds you have. So to have a look at literature, look at the NMR profiles and see where the peaks absorb. In this case, the Licrysum species are known for the chlorogenic acids, which are a whole group of compounds that are very similar, and they form dimers and trimers and single ones. So these group of compounds are well known. So this gave us an idea of this might probably be some of our chlorogenic acids. And the chlorogenic acids are also known as very biologically active compounds. So if you look at these two plants, this plant will not be active at all, where this one will probably have very good activity. So this already raised a lot of questions on how the metabolism of the plants were affected. If a dry region is going to do this, what will happen if our global warming or the climatic changes all over the world is changing? if it's becoming drier and warmer, will we probably have something like this in all our Helichrysum species, that you have a decrease of this. And these raise important questions when you start to look at your plants. So another functionality is to superimpose them. So it's the same two samples or the same two analysis. What you must make sure here is that your TSP peaks are aligned and that they are the same height. So so that you can compare the profiles of the rest of your analysis. So once again, like the one we had a look at yesterday as well, it's not all the samples of the dry ones that are higher. There are some higher and there are some lower. The same with the wet areas, some are higher and some are lower. And this is what you find. If your analysis is not run well, or there's a difference in your concentration, or when you didn't weigh off properly, then all the red ones will be higher and all the blue ones will be lower. And that will give you an idea of that something is not right. So then you have to go and check again. If all the peaks are higher in one sample and all the peaks are lower, it might be that the one plant is just lower in compounds, but you do not really find all the peaks in one higher and all the peaks in one lower. You often find something like this, that some peaks are higher, some are lower, and that the profile is more or less similar. So, as I mentioned, the Helichrysum plants are well known for the chlorogenic acids. So this is what you find in the human metabolome database. If you put in chlorogenic acid, this is the structure of chlorogenic acid. And you can see there's an aromatic ring there, but also other things here which give rise to these other peaks. But your aromatic ring is giving rise to all these peaks. It's 7.6 and so on. This one at 6.3 is the hydrogen there. This one at 5 is this hydrogen there. And these ones is then linked to the ring. So, but this part was the part that we were interested in, because this kind of looked like if it could be the peaks that we are looking at. So this is then screenshots of Kenomics again. And I've just made the blue peaks. These are the database peaks for chlorogenic acid. I made them a bit smaller so that you can see how they align. And you can see that once again here, you want to check the shapes of the peak. This J value must be the same as the J value in your sample. If there's a doublet, you would expect a doublet there. Same here. So here it's important. You can see that J value is different from this one. So if this was a broad one here and not like this, then you would say no, it's not the same. It's not the same compounds. Probably very similar, but this will tell you that it's probably not the same compound. So when we overlay this chlorogenic acid peaks with our sample, it's very probable that there is chlorogenic acid in there. All the peaks align nicely. The shapes and the J values looks very similar. But you can see there's other compounds as well. So it's not only chlorogenic acid. So chlorogenic acid is probably giving us an idea, but there are many other compounds, and you can see very similar ones. Many of them with doublets there. There are probably other compounds with a doublet like this as well, and they overlay a lot here. And this you probably find because it's aromatic rings, which are very similar. It's different compounds, but they are giving peaks in very similar areas. So there's also probably another one, a very similar compound. And as I mentioned earlier, the Helichrysum species are well known for the chlorogenic acids. So two of these chlorogenic acids will combine to form a chlorogenic acid, dicathlochronic acid, or a tri, and this is then probably what we see here. So it's very similar compounds, but the peak area or the peak profiles will differ slightly. You can see there that the doublet is moved to this side. So it's probably because the structure is slightly different. So here is just another one where I just match the peaks on the same height. So here you can see it looks quite good if you compare them, even though there are many peaks around them. You can check all of them should be there. If this doublet was not there, then it was not chlorogenic acid. Or if this one was not there, then it's not chlorogenic acid. If that one was maybe moved there, then it was very similar, but not chlorogenic acid. So once again, if you check all these peaks of this compound, then it will give you a good indication if it is this compound or not. If a peak is missing or it's shifted, then it is not the same. And I'm not showing the other peaks here, but these regions, especially with chlorogenic acid, give a good indication if you are looking at the same, because they have this broad multiplets in this region, which in this case was also present at 2. So we were quite confident that we are looking at chlorogenic acid. Okay, before I go to the last example, any questions on this?
I don't see any hands raised, Prof.
Okay, I hope it's because it's clear and it's because because I lost.
Yeah, can we get a show of thumbs up perhaps that you are still following?
I'm just surprised that they were excited when are we seeing the compounds.
Ndolo, you have your hand raised up. I see quite a few thumbs up, Prof. So
Okay.
it looks like people are following.
Okay.
Ndolo, you can unmute.
No, it's okay. Just trying to show that I'm following up.
Oh, okay.
Okay, good. Good. Good news. Thanks.
Okay.
So the last example I want to show you is we're going to take it a bit further. So in this case, we've now identified or annotated, not really identified, for instance, the chlorogenic acids. In the previous samples, we, for instance, annotated trigonelline, and we have sucrose and probably trehalose. So now you start to get an idea of the compounds that are in your samples. And if you can match these with your contribution plots, we showed in the previous session the contribution plot. For instance, these samples, I'm just going to go back. Your contribution plot, our contribution plot had huge peaks here, showing that this was different from that. But we didn't even needed the statistics on that, because you can just with the naked eye see this, but these areas or these bins of this was positively associated with these samples. So you will try to link your NMR bins then with the peaks of your compounds, like in this case. So if you have a bin at 7.6 and your bins at 7 and so on, so then you will try to link your bins with the peaks of your compounds. So this is an example. I'm going to end off with this example, which was done on pelargonium. It was an irrigation and fertilizer trial, nitrogen fertilizer trial. And pelargonium is a well-known medicinal plant. It's used, this Pelargonium sidoides is the ingredient for one of Europe's best-selling cough medicines. So it's commercially available. It's a well-known plant used in many formulations, but it's all wild harvested. Very little of that is propagated and cultivated. So we started to look at, if you're going to grow this in a commercial farm, you'll probably have irrigation, you'll have to fertilize to make sure the plants grow well. And what will it do to your plant? Obviously, the first thing was that we wanted to look at the secondary metabolites, because that is linked to your medicinal activity. but we were thrown off track with this project. So what we saw was that the irrigated material obviously was growing much better. We had a much higher yield, but we did not have a lot of nitrogen absorbed. So the plants, they took up some of the nitrogen until they had, let's say, enough or meet the requirements of the nitrogen in the plant, and they did not absorb more or taken up more of the nitrogen that was to a certain level. Whereas in the dry material, it was just not, it was less water irrigated with. The plant material was not, the yield was much lower, so the plants did not grow well, which we expected.
Prof?
Yeah.
There's a question on how to find the chemical compounds pathways in the plants from the NMR results.
Okay, yeah, I'm going to come to that now. So yeah, let me just explain this and I'm going to go back to that. Okay, so in this dry ones, we had a lower yield, but in this case, we had a much higher uptake of nitrogen. So, which was not what we expected. You expect the irrigated ones, the ones that grow well, to take up much more nitrogen than the dry ones. And that was the question here. Why do we see that? Why is the yield lower, but the nitrogen is increased? So we did what we did in the previous ones. We had a look at the profiles. We had a look at the contribution plots, the NMR regions that was of importance. And we started then to look to match them with compounds in the human metabolome database as well as the kinemix. And all the compounds that was linked to the contribution plot were all primary metabolites. So the secondary metabolites were not any different at all. No differences there, but we found that all the contribution plot areas were linked to primary metabolites, which were these ones. So sucrose, xylose, glucose. Once again, NMR is quite suitable for identifying your sugars. So this was nice. You could see the aromatic protons each time clearly separated from the other peaks. Citrate and quantitative, well resolved also. So these were the compounds then that we find in the irrigated material and the NMR. So then you have to find out, now you have 5 compounds which were quite distinct from your dry samples. But what does it mean now? And that's where you then get to your pathways. So now you have to go and check your compounds and fit them in pathways. And there are quite a number of databases and software programs that you can use. For instance, if you use the cake database, you put in, for instance, sucrose and xylose and glucose and citrate, and it will give you the possible pathways where these compounds fit in. So this was quite easy because the citric acid cycle is well known, that we know that gluconeogenesis produces a lot of glucose, or your sucrose, sugars. So this was a nice, easy one to follow. So the compounds in your citric acid cycle is increased, which means that you pump out a lot more glucose or your sugars. So this was quite nice. So this was an easy one. So, the basis of this was, we started with the contribution plot, look at the NMR regions on a contribution plot, then match it with the compounds that match that positively associated NMR regions. When we got the annotation of these compounds, then you can start to put it together and to see where it fits in a metabolic pathway. So this was easy. The dry one was a bit more tricky. So these compounds that we have here was down-regulated. These were quite low. But what was increased was asparagine, arginine, glutamate, your amino acids was increasing. and GABA, aminobutyrate. So when you're going to put this into a database to check for pathways, you will get quite a few, because there's quite a bit of interaction on these, on the how these ones are formed in your plants. I mean, there are various pathways. And the one that we started to look at was the alanine aspartate glutamate metabolism, where all these are linked. And what happens is your quantitative is pushed out of this cycle into glutamate and metabutyrate, which can then feed back into this sample if this is not accumulated. But in this case, it was accumulated, so this feedback is not present, and these compounds were increased, and now it made sense. So all the nitrogen that was taken up by this plant was not for growth, it was put into these amino acids. And all these amino acids are used as buffer compounds, or compounds that mitigate stress in plants. GABA and asparagine and arginine well known for mitigating stress. So this plant was taking up all this nitrogen to make sure it can survive this dry condition. So it was not using the nitrogen for growth, it was using it to put into these stress compounds. And arginine, asparagine, arginine, glutamates, also quite easy to see on the NMR. They have very nice, very well-defined peaks, especially asparagine. So it was quite easy to annotate the compounds as well as to compare them between the different samples. And by using metabolism or the metabolomics, we could get an idea of the metabolism of the plant and explain the unexpected results of the yields and the nitrogen uptake of the plant by putting all of this together. So yes, we wanted to have a look at the secondary metabolites, because that was the idea, to see if it was something. But we realized in this project, plants must first survive, and that is the primary purpose of the plant first. So if you stress a plant, before it can think of going into secondary metabolism, it must first survive. And this is exactly what we see here. So the major compounds in the plant and the differences were in the primary metabolites, not the secondary metabolites. And yeah, so this was a nice story to have at the end, to explain why we do not see a difference in the secondary metabolites, but in the primary metabolites. Okay, so this is just an example of when you get your compounds, then it's important to go further and try to then link it up with pathways, which then can tell you a bit more then about the plant and the way the plant reacts and the metabolism of the plant, which then give you a much better idea and answers on the things that you see in the field.
Okay, thank you. Prof, I just want to check with Mohammed. Do you feel like we've answered your question? Okay, he'll probably reply in the chat, but we can continue.
Yeah.
He says not much.
Okay. Yeah, well, maybe you must just unmute and then we can maybe just explain.
Mohammed, if you can unmute and indicate to us what is still missing for you, or what are you not grasping?
Okay, I think let me just do the last slide. There's a conclusion, and then we can go to the discussion session.
Okay.
And, if there are questions, maybe there are others that's also missing what I was just discussing there. Okay, so in conclusion, what I've tried to present here is things that you can look at, pointers that you must take note of when you're going to interpret your data, so that you do not get lost in your data and get sidetracked by things like bad resolution or outliers or things like that. So importantly is resolution, and linked to that is the quality of your sample preparation. So it's important to know that what you've done on your sample is 100% correct. Your analysis you get is accurate of your chemical profile. If you have good resolution, then that should be a true reflection of your NMR spectrum. So that is the basis of the whole thing. You can use the stack or superimpose functionalities in Metronova. I think most of the software programs got functionalities like that. And it's very nice then, after you have seen your, or after you have received your contribution plots, to go back to your analysis and then go and check those regions specifically. And if you have differences in, for instance, your treatments or the effect that you investigate, then those contribution plot NMR bins will direct you to the areas that you have to go and search for. So then the next one is then to go and find the peaks that match your NMR peaks, or your especially the ones in your contribution plot, using databases such as the Human Metabolome database and also published data. The Human Metabolome database is a good start, but if it doesn't match exactly, don't force it and just don't lie. Go to the literature and then see papers on similar compounds or compounds like that, or papers that describe the metabolism of those compounds. It might be that it's not that specific compound, but a similar one in the same pathway or so. So when you start to delve into the published data, then you start to get a better idea of what can match the peaks of your NMR. Then it's important to check all the peaks. So there are a few checks that you have to do. Look at the chemical shift, the splitting patterns, the peak shapes, if all the peaks are there. So there are a few things that you have to check to make sure that you do not lie to yourself and to everyone else. If the peak is not there, it cannot be that compound. It cannot be that the peak just disappeared. It must be there. If it shifted, then it is a possibility that it's part of the extract, or that the pH is a bit different, but that needs to be checked then. And once again, if you have something like that, then you probably need to go and check another analytical method to make sure that what you are looking at is correct. If you try to publish, they will in any case require that from you as well. So that people are quite strict on that. So when you annotate a compound and you want to go to identification, you have to either use another method or isolate or spike. Okay, so if you have your compounds annotated, then you can go and have a look at your metabolic pathways and the metabolism, and then try to get a bigger picture of what's happening. And here you can also then go back to the compound annotation. If you have peaks or compounds that do not really fit in the metabolic pathway, this can also give you an idea. Go and search for those compounds that should be in that metabolic pathway, and sometimes you can get an idea there as well of the peaks that should be there, or the important compounds. So maybe you annotated a specific compound, but it's maybe one similar that fits better in your metabolic pathway. And after you've put all of these things together, then you can start to answer your biological questions. And if you've been true to yourself and honest in all these steps, then you can be quite sure that you answer the biological question accurately and without making wrong conclusions on your samples. Okay. Okay, so that is my presentation.
Thank you so much for that, Prof. Very insightful, and I think everybody has learned quite a lot. Are there any questions? Mohammed says that he did actually get the answer from you, so that's okay. He follows now. Are there any other questions from the delegates. Okay, so we are currently at 1:20 p.m. So I'm just going to go through a few of our announcements. We will be posting a feedback survey. Please complete that for us, as I've mentioned before, that it really assists us with getting much of the resources that actually helps us in delivering these workshops for you. And it also helps guide us in sort of better defining or reworking our workshops. So please do give us your feedback. At this point, I think we have shared all the relevant links, documentations, requests for books in the chat. So most people should have downloaded that by now. But if there's any material that we've missed, feel free to contact myself, Prof Prinsloo, or Anza or Keke, and we will distribute that material to you. A reminder to everybody to please register or subscribe to our YouTube channel. Once you have subscribed, you will then actually get notifications once new material is uploaded. I've also added to this current chat one of our past recordings where we also had a webinar done on NMR metabolite profiling. So that's one of the recordings that we did with Dr. Shane Mason. So I've also posted it in the chat. And then, of course, the main and final announcement is that as I've mentioned, in October, we're looking more or less at the 14th or 15th or closer to that date for having our symposium. It will be a 2-day symposium. It will be a full day program, probably starting from 9 till 4 p.m. with breaks in between, of course. We are looking at addressing some of your requests, specifically the request to do molecular networking, more of the data mining. There will be a segment on quality control of your data and validating your models. And we are then looking at having somebody speak on some of the clinical applications of metabolomics, hopefully in an untargeted and targeted manner. And we also, of course, plan to have some of the students from the different institutions showcase some of their results. So we will have some of the students presenting in some of the slots. The call for those abstracts will go out shortly. So just to sum up then, in terms of this workshop, we started out looking at the principles of NMR, where Prof Prinsloo basically explained concepts such as the chemical shift, the splitting patterns, and how to basically link your structures of your molecules to the spectra that you're seeing. We then also looked at how samples are prepared. And I want to remind everybody that it comes back to what you put in is what you're going to get out. So if your sample prep is all over the place, it's not standardized, that is the type of data that you are going to get, and you are not going to be able to interpret that. So please be cautious about how you collect your samples, how you handle your samples, and then of course, the sample prep for the actual extraction. Please be very meticulous about that. And as researchers, a reminder, especially to the students on here, it is important to keep a lab book. You need your lab book to document the smallest little change, whether it's, on this day, I did this experiment, write down the aim of what you were doing that day, write down everything you were doing. So if you made a little mistake and you added 5 microliters extra, add that, because when you come back to your data, it's going to be a little reminder for you. Then, of course, once we've prepped the sample, we actually ran it on the NMR, and then we got data from that. So this morning, we actually dealt with how do you handle that data, and we've seen how using the software this morning, the different steps in pre-processing that data. So we went from the raw FID file that you actually get after NMR analysis to referencing your TSP, which is your internal standard. And then we actually normalized to our TSP peak. We then did phasing, and then we did binning, which eventually brought us to a data matrix. And that data matrix, we then took over to Simca, and we actually did the statistical analysis. Prof then went on to do the interpretation. So what is it that you do with this, the results that you get from the SIMCA analysis? The softwares that we used in this workshop, you can just Google SIMCA and you should be able to get a link to a free download. I'm not sure what the latest version is. And then also the Mestranova software. You can just Google it and there will be a link. But Anza Okeke, you can also just post a link for our delegates if you are still online, just for them to then utilize that. And then, of course, the documents that Prof Prinsloo supplied has some examples in there and some flow diagrams as to how to use the software. So remember, all of it is not set in stone. You have to optimize your experiments. These are just general guidelines as to how to use them and how they typically apply it in their analysis. I do see a hand up, Ndolo.
Yeah, thank you. Thank you a lot. It sounds that we are closing, but I have a very burning question.
Okay.
First Ndolo is in Botswana, in the University of Botswana. I'm doing my PhD here.
Okay.
I'm working metabolomics on the health science, which is schistosomiasis or bilharzia.
Okay.
But then I got interested when I learned about this workshop. But let me point 2 points. One, it's in alignment with one of the SDGs, number 3, which talks about good health and wellness, more so that you talk about trees or those from plants, metabolomics from plants. But then the question or the challenge is Africa, not just South Africa or Botswana, but Africa, we are all trying to be shifting from a resource-based kind of economies to a knowledge-dependent Africa. But then it starts like we are doing, capacity building in cases like, more especially, analytical techniques like this, which are not that much common. If you look at Africa in general, you find that there are just few countries which have got NMR. Either Botswana there with one, which I think they just bought it in a few months in the University of Botswana, and then some in South Africa. Now the question is, the main objective of this workshop or the platform, this training, is it that Professor Prinsloo thought of, or you, the facilitator, that when you invite, I think the first day we were 102, and today I can see now we are 59. But then from a broader point of view, one would wonder, why would you want to see us seated here, listening to this good presentation? What is in store for a learner or a student who is not basically in South Africa, who have to have access to UNISA, to these resources? I'm simply saying this because this is a way of saying you bring some motivation to other people to say, but this can be done. There are so many things that can be done, but we need to appreciate that as Africa, we are resource limited, just as I've pointed out earlier on. And that's one main challenge for African children. 2, the funding, it's one limiting factor for an African child, which then I want to know from this presentation, funding, limited resources, even collaboration as such. What's your planning? When you started this workshop, what would you say about all those things if some of the participants here willing to say, I want to do some work with these people, but restricted by those things that I've just mentioned? What would you do, or how would you help in such issues? The other thing that I would like to touch is, I think I've just enjoyed this more so that I'm working on metabolomics, and I don't know if you are going to share the recordings that you've been doing, and if the professor is willing to share contact and make it just clear if he's willing to collaborate with learners outside the UNISA who might want to start working on this area. I think that in that let me take this opportunity to say thank you for the workshop. It was just an eye-opener. It has actually helped me in interpreting my mass spec, more especially when you get to the meaning to those graphs in the where you were trying to talk, where you were talking about the PCA, the PLS. Actually, I've just changed. When we were teaching, I looked at 3D descriptive, and it quite helped me to see how a different view of my metabolites when I was seeing them on, whereby I was just using a scatter plot without using the 3D. The 3D that I just showed Prof using here, and then I tried it here, and it really gave me a good look of how my metabolites are grouping together. That's why I'm saying, will this be shared recording? So thank you a
yes,
lot.
thank you for that, Ndolo. So yes, obviously, Metabolomics of South Africa. So I'm gonna speak a bit, but I'm going to ask Dr. Fidel also to step in after me, as well as Prof Prinsloo. So if you go to the Metabolomics Society, Metabolomics South Africa page, you'll see that our mission is to promote the growth and development of the field of metabolomics, obviously. So mostly in South Africa, because I mean, in the developed world, there's a lot of machinery. They have access to all of this. So our aim is then also, how do we do this? How do we grow or develop the field of metabolomics? Is to promote and facilitate relations among the scientists that are actually doing the work. So we want to, by doing these workshops, of course, you can see that a lot of institutions, not just in South Africa, has signed up, right? So already there we are facilitating connection between academia. The partnerships that we have, for instance, with DIPLOMICS, ACGT, all of that. So it's not just connections between academia and but it's also between academia, government, and we are extending our hand and moving into, you know, bringing in more of industry as well. So the idea is that we sort of network and everybody is familiar. So what we're trying to do also is that you become more familiar with who is doing what, where are the resources, who can I contact. And in this way, with improving this metabolomics research profile, you knowing, for instance, Prof Prinsloo works on plant metabolomics, I work on human biofluids, you already have an avenue. So if you are struggling in your work, you have resources that you can reach out to, right? So the idea is not just to have the workshops and it ends there. So the idea is that we are transferring skills right now. So it has assisted you in completing, or this workshop will likely assist you in writing up your dissertation quicker and completing your degree, right? It might assist you with interpreting data that you might have struggled for the longest period of time. So the idea is skills and knowledge transfer. And in that, it doesn't just stop with us. So you now have been educated in something that you might have lacked. You also need to do your part by continuing. So we expect you, with the knowledge that you have gained here, to do your little workshops in your own institution, in your country, start up your own little workshops, reach out to us if you need assistance, but take it further. So it's much like DNA replication. So we go from, you know, we've given you the information, the code, we're deciphering it, and we're making protein. So the protein is that knowledge and skills transfer. So let's continue with that DNA replication, transcription and translation into a final product. So the idea is, with us also connecting academia, government, and industry, is that we also get to speak about what is needed. What can industry do in terms of finances or resources? What is it that government can do so that we don't have this lack? The idea is also that if we can show that there is a great need, and, you know, metabolomics is not just assisting in terms of research from an academia standpoint, but it actually has clinical real life application, we can get, you know, government or industry to you know, assist us in these grants and getting more of this instrumentation in as well. So it is a joint effort. So my take home would be that, yes, we have this platform and we are transferring skills, but as much as we are transferring, we need to collectively continue with driving this transfer of skills. So I hope that answers your question. So you can also go to our MSA homepage, which specifically then sort of lists our mission as well as our goals. So in addition to you know, the graduates and the papers, or the graduations or the dissertation that you might end up writing, of course, you'll also get publications from this. So all of this collectively adds to what you are doing. And that is why we also ask you to complete the feedback surveys. So if you write to us, and we also want to encourage you guys, if these workshops actually helps you with getting your degree done or your dissertation done, please let us know, because we can then write to a company and say, you know what, this has really assisted 50 students in graduating in a shorter period of time. You know, these techniques, these instruments are valuable, and we can come to agreements where they could probably subsidize an instrument and stuff like that. So it's a bigger picture that's at play. Dr. Fadal, I'm not sure if you perhaps want to add, or Prof Prinsloo.
Thank you, Aurelia. That's really a relevant point that Ndolo raised. And as you said, if you visit our website, the website or other online platforms, you will see the mission of the Metabolomics South Africa. It's not only limited to South Africa. The idea, the dream is to expand to other parts of Africa. Metabolomics in Africa is still very young, and actually across the globe, metabolomics still young, 20 years old type of field. It's growing. In overseas, there is quite a lot of resources. They are more advanced, and they have funding and makes things much easier. But it's not something that is not doable here also in Africa. It's possible. Metabolomics is growing. What we have just seen, the workshop from the team from UNISA, it's really great work that is being done there. And Northwest, the same. So it is possible. So if you attend the symposium that is going to happen in October, we give kind of overview of the status of the metabolomics in MSA. And possibly also we touch on those potentials of collaboration, invitation for grant application, joint grant applications. So reach out, and it's possible that wherever you are, it's not impossible to do metabolomics. The resources are limited, but they can be expanded. As Aurelia said, we have a subcommittee that is industry partnership subcommittee. The mission is to reach out to the industry, to the government institutions, to forge the network and the collaborations, which can be a channel through which funding and other resources can take place, can happen. So yes, there is a need. There are quite a lot of needs, but it's possible that bit by bit we can get things done in wherever you are.
Okay.
Prof Prinsloo, if you have something to add on.
Yes, I think you touched so many important aspects that is very, very important. For me, unfortunately, we are sitting here at the southern tip of Africa, and we are isolated. If you're in Europe, if you're in Netherlands or Belgium, where you have countries all around you, within 200 kilometers around you, you can have access to any equipment and any university and any resources. We don't have that. So we, in South Africa, when we started with metabolomics, we got stuck in 2012 because we did not have expertise, we didn't have equipment here. So where did we get help from? The Netherlands. And now we are about 10 years later, and I think it changed tremendously. And I'm so grateful for that, because the reason, or the fact that we are in Africa, in the southern tip of Africa, doesn't mean we have to stay behind. And I might be sounding harsh, but I get frustrated by researchers in South Africa, now specifically, that is stagnating with research with students. They're doing the same things over and over and over and over. When I was an MSc student, it was exciting to do biological assays on bacteria. People are still doing that and just sticking by that. We have moved way beyond that. The world has passed that stage 20, 30 years ago, and we are still continuing with the same things over and over. I feel we're scratching the surface the whole time. We're taking our plants, indigenous plants, we do an assay, antioxidant, we do a bit of antibacterial assays and so on, and then we write up for MSc. We never go beyond the surface level. And if workshops like this can make us realize that there's a bigger world out there, we are competing with them. We want to publish in the same journals, but we are so comfortable in what we have been doing in the past 20, 30 years, and people want to stay here, and it's not going to work. If we don't realize that we have to work together, all the countries here around us in Africa, and develop ourselves and use the resources that we have, we are going to stay where we are. And we are going to get further and further and further behind. When we started with Metabolomics here in 2012, Netherlands was already doing that for 20 years. So at that stage, we were already 20 years behind. So we have made great strides, I think, in South Africa, but there's a lot more work to do, and it's important. I hope there's a lot of students here. I hope there's a lot of young academics here that get new ideas on how to transform our research in our country. It's good to use things like bioassays and antioxidants and whatever, all those assays that we are doing, reverse transcript and so on. But there's so much more. We can do so much more with the equipment that we have. If we just reach out a bit and look a bit further than the easy things that we do and get on par with what's happening internationally. We should not be behind. Why should we be behind other countries? Why we should be behind Europe? We have NMRs, we have LCMS, we have expertise here. So yes, I mean, this Metabolomics South Africa, Aurelia, Fidel, they're working very hard to get metabolomics going and to expand and to draw in other universities as well. There are a few universities that's doing it, but it's important that we expand this base and expand this network between universities. So we are doing NMR. We have gained some experience. We do not have a lot of experience on LCMS, so we collaborate with LCMS. If you are doing metabolomics in your country, if you need assistance, then you know where to knock on now. And I think the people that are trying to build this Metabolomics South Africa is really trying to reach out to people that need to get assistance or that want to improve. So I think the chances are very good that you will get assistance if you reach out to any of the people that are part of this Metabolomics South Africa. And I really hope that these workshops and the work that people like Aurelia and Fidel is putting in is going to deepen research and improve our research questions and our interpretation of our data to a deeper level than just scratching the surface and just trying to do the least possible to fill up pages of a PhD or an MSc. We can do better, and we should do better if we want to be on par with international researchers.
Thank you, Prof. So just to add on to that, Ndolo, we will make available, as we said, the YouTube page, the Metabolomics South Africa YouTube page. We've posted the link several times. Anza or KK, if you can maybe just post it again. Please subscribe to the YouTube channel. When you subscribe to the YouTube channel, you'll get notifications. All our videos will be uploaded there. So our website is being reworked. It is up, but we're updating it. So what we will list under the website is a profile of the different institutions where metabolomics is being done. And you'll get an idea, oh, UNISA does more plant metabolomics, Northwest does more human biofluids, UJ does both, or a mix of, metabolomics research. So you'll be able to sort of click and read on those profiles and what the different institutions are doing. And you feel more than, free to contact us. So we've made available our email addresses. I think it was posted earlier in the chat as well. We've even said when you are on our YouTube page, those comments that you post there, we will do our best to also address questions on the YouTube channel, any questions that are posted there. So you do have access to us. Please make use of that. Okay. All right. So yes, Anza has just posted the YouTube link. All right, if there are no further questions, I think there's just a few people that have said thank you. It's been very informative. They did learn a lot. That's Mohammed, Nasha, Kamati says, thanks, Prof, for that point that the culture of working in sailors is bad. Yes, so overall, I think we've had a good workshop. And with that, I will hand over to Dr. Fidel then to do the closing if there's nothing else from your side, Prof.
Yeah, no, I'm happy. Thanks. Thanks to all the organizers, ACGT, DIPLOMICS, Metabolomics South Africa. Thank you for the good work and for creating these platforms. And as I say, I hope it's going to grow from here stronger and stronger and build more networks and collaborations from here. But thanks a lot for the opportunity.
Pleasure. Over to you, Fidel.
Thank you so much, Aurelia. And really thank you for coordinating this workshop. It's really informative, and it's so great to see the number of attendees and the interactions. And I would like also to thank the team from UNISA, Gerhard and the team. You really provided great informative insight. And I like the way you went from the basics to the interpretation of the results in a biological context. And it's then up to the attendees to ask to go and practice. And the contacts are there if there is any question. And I would like also to thank Keke and Anza, who are working behind the scene to make things run smoothly, the communications and all the technicalities behind the workshop. Thank you so much. You are already noticed.
Definitely.
Yes. And for all the delegates who attended, thank you so much. And as Aurelia pointed out, there is a symposium coming up in October where there will be also some training touching on certain aspects, possibly more on either MS or NMR-based type of analysis, and also to see different research that are being done in different institutions. And also it's an opportunity, it's a platform where networks can be forged, created. Please, once you see the call for registration, please do register. And those who are not yet member of the Metabolomics South Africa, even if you are not in South Africa, please feel free to join. If you are not sure how, you can really drop an email to Keke and Anza, and the ones who have been communicating with you. At the end, I would like also to thank DIPLOMICS, ACGT, UNISA, and all the institutions that really came on board to assist to make this workshop successful. So there will be more workshops, training, webinars that will be planned ahead in the future. And please stay tuned and see. Interact with us also via different online platforms, and let's get Metabolomics growing. Thank you so much.
Thank you, Fidel. I saw one question. So if you go to our website, there should be a tab where you could click on, I think, a member link for signing up. But if not, just send me, because the website is under construction, or we are reworking it or updating it. I have sent my details. Please just send me an email reminding me that you want to become a member, and we'll send that details. I've posted my email address on the chat. Okay. All right. Thank you, everybody. Thank you so much, Fadal. Take care.
Thanks.
Bye.
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 Thank you.
Bye, thank you.
Okay.
Bye.
Thanks. Thank you, thank you.
Wow, thanks a lot. Thanks a lot.